Hi, so I'm Jérôme, and AJ on the back is my TA for this tutorial. So I have to, per PyCon regulations, I have to read some introductory notes. So first, there is a survey link, which is here, in which I will show again at the end of the tutorial. I mean, only if I feel like you are happy about the tutorial, then I'm sure they will give good feedback, but if things don't go as planned, maybe I won't show the link again to make sure I don't get bad ratings. We will do a break at 10 a.m. Okay, this is confusing because the email told 10:20, but this says 10. So there will be a break either at 10 or maybe at 10:20, depending on how we feel like it. We will finish at noon 20, and lunch will be served in Oregon Ballroom 201 and 204 upstairs. At lunch, those with dietary needs should let the server know. And we have placed as much power as we could afford. Please share the outlets. Outlets could be in your row, or the row behind you, or the row in front of you. All right. So normally, each of you should have one of those little papers. If you don't, please raise your hand, and someone will magically drop from the ceiling using those fancy ninja ropes and give one of those to you. This little paper has the IP address, login, and password to a virtual machine to which you will connect if you want to do the hands-on part of the workshop. And that being said, we're going to start with the content per se. So those slides are available online. If you go to container.training, you will see a little menu which shows the extent of my HTML skills, i.e. not much, and which lets you see those live slides. There is also a link to download a PDF of those slides, and the PDF has some extra content. I do two versions of this tutorial. There is the half-day version and the full-day version. And so the PDF also has the content for the full-day version if you want to get even more Docker stuff when you walk out of this. So logistics, all right. There is an instant messaging system. A while ago, we did a tutorial where the conference had a Slack set up for the conference, and we had this wonderful idea, oh, what if we created a Slack channel and invite people to join in so they can ask questions and give feedback and so on. So we did that, and it was extremely useful, and so after that, we decided to do that for each tutorial, except setting up Slack is kind of complicated. You know, you have to go to this form and you put your email address and you get an email and you have to put the password and everything. So it's kind of slow and annoying to do that in the beginning of a tutorial. So instead, we're using Gitter. Gitter is a small messaging platform which is tightly integrated with GitHub. So if you have a GitHub account, joining a Gitter chat room is literally one click. Like, for instance, if I click here and then on that link, it drops you into this chat room, and you are welcome to give feedback, ask questions, comment, and everything. And obviously, I won't be able to simultaneously show slides and do demos and explain things and read that, but AJ on the back will be monitoring that if you have questions. If you are more on the shy side and don't want to raise your hand to interrupt me or something, feel free to ask on Gitter. That's what it's for. Okay. So the tutorial is broken down into two parts, which are almost of equal size. The part one, I will explain what's Docker, like give you a high-level overview in a kind of elevator pitch if you need to convince people that they need to use Docker, or if you need to convince yourself because you're here because your coworker, boss, or someone told you, hey, you have to come to this thing, but you don't know yet much about Docker. Then I will tell about the virtual machines that we have. I will explain how to install Docker if you were so inclined, like to install it on your own machine. Then we will run containers. We will run containers in the foreground, in the background. We will attach and detach to containers. I will talk about Docker images, the difference between a container and an image. Then we will build images. We will see how to write Docker files, which are recipes to build images. I will give a little example of what a Docker file for a Python application might be, and a kind of a good example, bad example, to give you an idea of what kind of gotchas you have to be aware of when writing Docker files. I will talk a tiny little bit about the Docker Hub. Then in the second part, we are moving more to a kind of slightly more ops side of things. We will see how to name and inspect containers. We will see how to connect containers together, how to manage storage with volumes. And then we will see what a local development workflow with Docker looks like. And I will wrap up by talking about Compose, which is something to assemble multiple containers together to make a more complex application. All right, let's get started. So first, I want to give you a kind of high-level overview of Docker. Either like if, again, you need to be convinced about the interest of Docker, or if you need a kind of a ready-to-use pitch, if you need to convince others. So first, there is like the not so technical version about why Docker and why everybody is getting so excited about containers. The idea is that the way we build software has changed. You might have heard about monolith versus microservice. We used to build applications like one huge chunk of code that gets deployed on one server. There is a really long development cycle. We write specs, then we implement them, then we test, and then we put to production, and you repeat, but the whole cycle could take months, sometimes even years. And when you need to scale up, you just buy a bigger server, and when you bought the biggest server on what that you could buy, then you're like, oh, we have to put this thing called a load balancer. How do we do that? So this was maybe 10, 15 years ago, but now things have changed a lot. Now we try to break down applications, maybe not as far as microservices, but at least in smaller parts that can be deployed independently. We try to iterate really quickly in software projects. There is this idea of the MVP, the minimal viable product, where you try to ship something as fast as possible, even if it's not perfect, even if there are flaws, and then you iterate, you improve as quickly as possible, maybe doing sprints of a few weeks or a month so that you can have a really tight feedback loop. And when you need to scale up, in fact, you scale out, which means instead of putting bigger servers, you just put more servers, because you can almost always put more servers. And stuff like load balancing is something that is built in the logic from almost day one, instead of being added as the last chance because you need to withstand insane amount of loads for your application. And in this context, deployment suddenly becomes very complicated, because before you just had like one server, one application to deploy on it, so the deployment was pretty simple. But now we have many components on many servers, so deployment becomes this kind of quadratic complexity thing. And there is this matrix from hell of software deployment, where you have all those components that we want to deploy. So your website, the API backend, the database, the message queues, and so on and so on. And those are all the environments where you want to deploy, like this Mac laptop, this Linux laptop, some servers in the closet, some VMs in the cloud, and so on and so on and so on. And so sometimes for one line or one column, there is a good answer. For instance, when you want to deploy, Python, now it's like, okay, we have virtual env, it can get you really pretty far. If you're doing Java, then there are jar files. If you are now like on columns, if you're deploying only on Amazon EC2, you could use EMI, like those Amazon machine images, that's great. But if you are outside of Amazon, they are pretty useless. And so we need something to address the whole range of options. And for that, we have inspiration from actual shipping containers. Well, we're actual shipping containers. The idea is that you divide the ecosystem into two halves. So in the upper half, people putting stuff in containers. So you want to ship something somewhere, you just put that in the container, and then you tell someone, okay, get this container from Portland to Amsterdam, or from Hong Kong to Los Angeles, or wherever. And those people move the container around. They don't have to know what's in it. You don't have to know how they move it. The container just goes from point A to point B, and you're happy and get stuff out of it. And vice versa, the people moving the containers don't have to know if the container has coffee or pianos, might be a little bit far-fetched, cars, probably not radioactive waste, but you get the idea. You get this kind of nice separation of concerns between the two halves of the ecosystem. We are pretty lucky because there is the equivalent thing in software. We have software containers where you can put code in this software container and then give that container to somebody else who will run it. And so when you put something in a container, you don't have to worry about whether that container is going to run on a Linux machine, on a Windows or Mac machine, on a virtual machine, in the cloud, or on this and this. And vice versa, when somebody gets a container and has to run it, they don't have to worry about, does this contain a Python application? Is this like a Django web app, or is this some Celery thing that processes jobs from a task queue? Is this a database? No, it's just a container, and they can run it any way they like. And this solves the deployment problem that we are talking about. So the end result is, so those are like the big, nice, impressive numbers. ING, a big European bank, went from 9 months from time to market for features to 15 minutes in the best scenarios because of that. I know that seems huge, but you can read the whole details if you want. So for CI and CD jobs, so using containers helped to kind of divide by 2 the whole time that it takes to run the whole suite of tests. And so that's the kind of result that we have. Now I want to give you like a more technical approach of things, because this is kind of high level, like, okay, putting software in containers, but how does that help me? So the first thing is to escape dependency hell. So you might be familiar with this process, like when you have to deploy some software, when you have to give instructions to someone about how do I deploy this. Say, okay, first step, I'm going to write a nice install.txt file telling them how to actually install my stuff. And then if I want to go to the next step, I turn this install instructions into a little script. And this script hopefully should work pretty much everywhere. Well, it should work everywhere as long as people have exactly the same environment as you have. If your script has apt-get install Python pip and then pip install something, if people are using a non-Debian distro, apt-get won't do anything. If they are using a Debian distro but it's not the same version, maybe they won't get the same version of Python, and down the road at some point you will have incompatibilities. So the idea is that with Docker, you can go to the next step and turn that little installation script into a Docker file. And the key difference between an install script and a Docker file is that in the beginning of the Docker file, you say from this. So you indicate what's the starting point for the installation process. So you say this script is supposed to execute in a Debian 7 system, or a CentOS 7.1 system, or a Fedora, and so on and so on and so on. So that way you can agree on the starting point, and all the instructions after that will work correctly. And then you can share that recipe, that Docker file, with anybody, and they can build it and run it, and it works. Another advantage which comes from that is that you can onboard contributors rapidly. So this means when somebody joins a project, there is like, okay, now we have to set up the dev environment. So before the container era, so to speak, if you did things really well, you have maybe VM images, maybe using Vagrant, and people just have to set up Vagrant, VirtualBox, download the Vagrant-based box, they do Vagrant up, and normally everything is up and running. And that's kind of almost the perfect scenario, but everything else is like, oh, those are the install instructions. Now you have to spend a few hours, a few days if it's a really complex project, to get everything up and running correctly. So with Docker, the goal is that once you have written the Docker files describing each component, and then the compose file which assembles everything together, anybody on any Docker install can clone the repo, do Docker compose up, and all the components are brought up and running and just work. So that's great. In particular, if you are working on many different projects and constantly have to switch between them, either because you are a contractor or because you work in a company that contracts for others, and you end up working on tens or even more projects. Another thing where Docker really helped a lot is to implement reliable CI pipelines. So in CI, one thing that you want is to have a clear test environment that is the same for everybody and that is really easy to set up, but also easy to tear down. So that when you want to run a bunch of tests, you have this clean environment so that everybody has the same one. You run the unit test, and when it's done, you throw it away so that you can put a new one for the next round of tests. And containers are great for that. And the time taken to set up a container and tear it down compared to a VM, it's an order of magnitude faster. It's creating a container is less than a second. So if you compare to VM plus VM boot time and so on, huge savings. All right, that's for the high-level pitch. A really brief history of container before we start to actually use them. Some people will tell you, okay, there is nothing new with Docker and containers. We've been doing containers for 10 years with zones and OpenVZ and jails on respectively Solaris, Linux, and BSD. If you really want to look at the first containers in computer history, you have to go to almost 50 years ago, IBM VM370. That's the first hypervisor, and that was in 1972. So next time somebody tells you containers are not new, yeah, they are really not new at all, because computers are not new, and we've been doing containers almost since the beginning of computers. Why? Because computers were a really expensive thing, so you don't want to have one computer, for just one job. So very early, we wanted to containerize those computers. So initially, the roots of Docker were in a PaaS, platform as a service hosting, and they were used as one of the components of this PaaS, so .cloud. .cloud was started kind of in 2008, and there was a little container engine, which was a small Python script, which slowly evolved into a kind of Frankenstein microservices monster. The .cloud platform in 2012 was 100 services. There was stuff to create containers, stuff to monitor containers, stuff to build images, stuff to update images, stuff to detect when containers go out of memory and then we need to fix them, and so on and so on. And at the end of 2012, the team in charge for that said, okay, we need to clean up that mess and do a big refactor, like the big refactor of hell, where you're like, okay, we're going to go through this tunnel of 3 months of development, we'll stop shipping features, and after 3 months, hopefully we'll get something better. And the outcome of that was basically Docker. So rewrite from Python to Go, something really small, something that would do just the essential things that you need for containers. And then the idea was, now that we have this clean piece, we can rebuild the platform on top of that. Except not exactly, a little bit more than 3 years ago now, in 2013 at PyCon Santa Clara, that's where in a lightning talk we announced the first release of Docker, and people were really excited about it. And basically the message was that .cloud stuff, okay, that's nice and fun, but Docker is way more exciting. So please stop working on .cloud and instead work more on that Docker open source cool container stuff. So that's basically what we did. At each cycle, so each month, we would take a few developers away from the .cloud project and put them on Docker, until eventually 100% of the engineers were working on Docker, and we got rid of .cloud. The first people using Docker have been people building PaaS, just like we had been doing before, because it's like, okay, you have two options. Either you build your container tool set from scratch and you spend maybe 6 months, maybe a few years on that, and then you can start building a PaaS. Or you use Docker, and back then it was very imperfect, it still is, but you get a huge head start over everybody who is just kind of starting to put their tools together. So people building PaaSes, people using PaaS but who wanted to build their own, people doing CI. It was kind of a nice coincidence that shortly after Docker was released, there was a bunch of startups wanted to disrupt the CI industry, kind of blossoming around and trying to disrupt existing other companies doing CI, and developers. Like Docker was and still is very Docker friendly, so a lot of people just liked it because it helps to solve a lot of problems. In 3 years, Docker's changed a lot. Like 3 years ago, when we said Docker, we meant the Docker engine, so just a little bit that runs containers. Now, when we say Docker, we mean the whole platform. So there is the engine itself, but Compose to assemble a bunch of containers together, Machine when you want to manage Docker hosts, Swarm to build clusters, to build a single cluster from multiple machines, and so on and so on and so on. There are commercial offers and a company behind it, but we don't care about that because it's money and money is dirty. And we're going to start with, speaking of dirty, getting our hands dirty with the VMs that we have. So everybody has got this little paper because some more people trickled in just after. So if you don't have this little piece of paper, raise your hand. No, everybody has it. Perfect. So we have VMs. So first, why do we have VMs? So the thing is that I wanted people to be able... Oh, you want one of those little pieces of paper, sir. So we wanted people to be able to experiment with Docker and try things. And so usually the kind of obvious idea is, okay, let's install Docker on your machine. But that would take away a big chunk of the time that we have now because we all have different machines, even though I see a huge majority of Apple laptops here. And so we wanted to be able to jump in immediately. And also when we will build container images, that will download packages from the internet. And if, like, I don't know, it's like 60 people in the room, if 60 of us download packages at the same time, that's going to take forever. So instead, we will just SSH over remote VMs, because those VMs have infinite bandwidth because they're in the cloud, right? So the first thing that we will do is that we will log into the VM. So I also have one of those VMs here. And nope, that's not it. That's here. So SSH Docker at the IP address. Make sure that you put your IP address, obviously, because if you put mine, there will be two of us on the same VM, and that's going to be weird. And the first thing I will do to make sure that everything is fine is Docker version, and that tells me I have the latest and shiniest version of Docker, 1.11.1. I will give you like a few moments so that you can log into the VM and do that first command. And then if you can, please raise your hand if it works. A vast majority. And now if you can raise your hand if it doesn't work, because, so 2 persons, yes. So you seem to be on the Wi-Fi okay. So 523911228. I'm going to give you another. Try with that one, maybe. Thank you. Okay. Okay. Want me to read it out? Yeah, sorry, it's really small. So 52.3.8.206.163.
Which Wi-Fi are you connected to? The 5G or the... Try the 5G.
Okay. So if we were to install Docker, how would we do it? Because sometimes people are like, okay, those VMs are nice, but I thought I would walk out of this with a working installation of Docker on my machine. So if we were to install Docker, if you are on Linux, we have upstream packages for every distro. And this is one of the few scenarios where I would definitely recommend that you use upstream packages. That means the packages straight from the Docker project versus the packages from the distro. For a couple of reasons. First, Docker moves super fast, and distros tend to lag a little bit behind, so you might get an outdated version of Docker, especially if you're using a stable or LTS version of your distro. The second reason is that, unfortunately, the people maintaining distros and the people maintaining Docker can't exactly agree on how things should be packaged. There are lots of technical reasons behind that, and so often it happens that the Docker packages of your favorite distros might be broken, especially if your favorite distro is Red Hat. So that's why for now it's better to use upstream packages unless there is a strong, compelling reason for you to use the distro's packages like support or something like that. If you are not on Linux, if you are on OS X and Windows, there is something called the Docker Toolbox, which is a kind of big bundle that comes with VirtualBox, plus a little VM running Docker, and a bunch of wrappers so that you can use Docker almost as if it were local. There is also something. So, for instance, when you are on a Mac and you do Docker version, you end up sending a request to the little VM running Docker, because everything with Docker goes over a REST API. So when we do Docker run to start a container, Docker version, Docker this, Docker that, each time we are crafting an API request, connecting to the Docker engine, sending the request, and showing the result. So when you are on a Mac or on a Windows machine, what happens is that you send that request over to a small VM running kind of under the hood in your machine. For instance, on this Mac, if I do Docker version, right, in that case, my Docker thing is not even running, but it tells me that my client is running on Darwin. Okay, and let's give it like a few seconds to come up. And it will tell me that my client is running on Darwin, so on the Mac, and the server is running on Linux. See, client, Darwin, server, Linux. Okay. We have something called Docker Mac and Docker Windows. This is something after the Docker Toolbox. If you're interested to be in the beta of this, it's a kind of better integration between OS X, Windows, and Docker. Contact me after the tutorial, and I can get you into the private beta for that because it's pretty cool. Something about security. When you have access to the Docker API, you basically have root access. Because when you can start a container, you can say, hey, I would like this container to have a lot of privileges on the machine. I would like this container to have full access to the hardware and this and that. So basically, if you can start a container, you can take over the machine. And it's kind of by design. And if that sounds weird, you have to think about, with VMs, it's the same thing. When you have full access to your VM hypervisor, if you want, you can start a VM that has access to physical devices as well. Your VM can have access to the physical memory, to some PCI devices, stuff like that. So your VM could also take over. Of course, if you control exactly how the VM can be started, like when you start a VM using a cloud provider API, then you get a subset of your hypervisor, and that lets you only start a VM within a given bounds. So the same way, if you want to do like some kind of public Docker service where people could start containers, you have to kind of put a filter between the Docker API, which lets you do everything you want, and what you will expose to people. So by default, if people have access to the full Docker API, they will be root equivalent, which is why when you install Docker, the Docker control socket will only be usable by the root user, which is why by default you will see a lot of tutorials and Docker documentation saying sudo Docker this, sudo Docker that, so that you can access this Docker socket. You can also put the user in the Docker group, which is what has been done on the VMs that we are using here. I see that my user is in the Docker group, and so I can do Docker commands without requiring root access. All right, and I've talked a lot, and we still haven't started any container, so we're going to change that. We're going to run our first container. So the hello world of container is going to be Docker run. Is this big enough, like for the people on the last row? All right. So Docker run, busybox, echo hello world. So when I do that, so I'm sending a request to the Docker engine to say, hey, I want to run a container, and I'm going to use the busybox image, and in this image, I'm going to execute echo hello world. So the first time I do that, it says, I have no idea what this BusyBox image is, so I'm going to query a public library of images, the Docker Hub, and the Docker Hub say, why, yes, I have BusyBox, and I'm going to send it to you. So I'm pulling the BusyBox image from the library. And then I'd say, okay, I downloaded the image, and it executes the echo hello world, and I just run my first container with an extremely simple command in it. If I do the same thing again, this time, the BusyBox image has been downloaded already, so it can execute it immediately, skipping the lengthy download phase. Well, not so lengthy because BusyBox is so small, but if that were a bigger image, that would be longer. BusyBox is this tiny kind of Swiss Army knife thing. It doesn't come from the world of containers. Generally, the first contact that you have with BusyBox will be with embedded systems like phones or Wi-Fi access points, things like that. Because you don't have a lot of storage space here, so you want a small tool that will have ls, grep, ifconfig, ps, and so on and so on. BusyBox provides all those usual suspects within a small compact binary. Okay, so that was not a very exciting container though, so we are going to start a slightly more useful container. I'm going to docker run. I'm going to add another flag, -it, which is just shorthand for -i-t, Ubuntu. So -i-t stands, so -i means input-output, and t means terminal. So it means I want to interact with my container, and the -t means I want a terminal emulation. So now, instead of being connected to my VM, I'm now root at some hexadecimal thing, so I'm now in my container. For instance, if I do top, I see that there are almost no processes at all, because I'm in the container and I only have the processes running in the container. In that case, is it still readable if I unzoom a little bit like that? Yep, okay. So in this container, so that's an Ubuntu container, so I can do a few Ubuntu commands, like I can do dpkg-l to see the installed packages, and I'm going to count the packages installed in this container. I see I have 100 and something packages in the container. Why am I doing this? Because I want to run the same command in my host machine, which is also Ubuntu, so dpkg-l pipe wc-l. So I'm counting the packages installed in my host environment. And in my host environment, I have like 650 something packages. I'm doing that to show that even though this is an Ubuntu container running in a Ubuntu VM, the two systems are completely separated. They have completely different packages. They have completely different versions of Ubuntu. And if I want, I can run a CentOS container on an Ubuntu machine, or an Ubuntu container on a coherence machine. Any combination is possible, it doesn't matter. All right, so now I want to run something in this container. Like I want to run Figlet, which will be the little sample that I will use in the next chapters. So if you don't know Figlet, you will know about it soon enough. So I'm going to docker run again. Then I do, so if I do Figlet, it tells me, okay, command not found. So I want to install it. I see, maybe I should, it's better if I put that on top of the screen. So I'm going to install it with the normal Ubuntu command, so apt-get update, and then apt-get install Figlet. And now I can do Figlet hello. And so Figlet is this wonderful program that lets you do ASCII art messages. So I use this container exactly as I would use a little server that I would create like that, and then I can install stuff in it. If I want, I can install Python, and then I can do pip install, and this is just like a normal server, kind of. So now, after doing that, I'm going to exit the container. So you can use like exit or logout or press Ctrl D. And I'm going to start it again. And now that I started it again, I'm going to do Figlet. And it tells me command not found. So is my container completely gone? Do I have to reinstall everything each time I start my container? No. So my container, the one in which I install Figlet, is still here. It's kind of still behind. When I quit the container, the processes stop running. So I'm no longer using memory and CPU, but the container is still here somewhere on disk. It's a little bit like stopping a VM in VirtualBox, for instance. Now there is a big difference in the way we deal with VMs and the way we deal with containers, and it's an artificial workflow difference, is that when you work with VMs, typically you have, let's say you have something like VirtualBox. So you start VirtualBox and you have a few VMs there. There is like maybe, there is this Ubuntu VM, there is this next version of Ubuntu because you're testing stuff, there is another project VM. And when you want to work with a VM, you start it, you connect to it, you install packages, you do stuff, and when you're done, you can stop it. And you know that the next time you need it, it will be exactly in the state where you left it. So it has a kind of a life over time. With containers, we try to push a different workflow where you have a container image, and each time you need a container, you just create a brand new container from that image. So that each time you start working with a container, it's a brand new container, it's clean, it doesn't have any leftovers from the last time you used it. So you might think, okay, but does that mean I need to reinstall everything each time? No. The idea is that when you need a set of programs in your container, then you build a new container image. You build that image, and then each time you need to work on a container like that, you create a new instance of that container. So at first, this could seem like overwhelming, like I have to create a new image each time I want something new in my container. So that's why we have some really good and efficient tools then to create the images so that this workflow doesn't become unmanageable. So why are we pushing that? You might have heard about the pets versus cattle metaphor, where so it applies to servers, where pets servers are servers that have an individual name. You know exactly what they are, which version they are. Like I have maybe those 5 PostgreSQL servers for different purposes, and I end up having different versions. That one is, most of them is running Postgres 9.1 because I all installed them with 9.1. But then at some point I upgraded a couple of them to 9.2. On another I installed like the geographic extensions. On another I have maybe some kind of attempt at replication, but I never really finished to configure it. And so it means that my 5 servers are completely different. And I can start to have some different behaviors on my servers just because they have different setup and different things. And one of those servers goes away, it's like, oh crap, I need to reinstall it exactly the way it was because it's different from the others. While if I deal with my servers as cattle, it means all of them are identical. I say, okay, all my stuff is using PostgreSQL 9.1, or if I need 9.2, then 9.2 for everybody. If I need geographic extensions, I'm going to put them everywhere. And at least, even if I have this single snowflake, I'm going to have a nice image, something that what I can create clone from. Like if one server has a problem, instead of trying to fix it, I can just create a new one, put the data on it, and go. So that's the idea in this pets versus cattle approach. When you have a problem with the machine, if it's a pet, you don't want to terminate it because you get emotionally attached to it. If it's cattle, you can, okay, let's remove the bad apple and just put a new one and go ahead. So that's the idea with containers. We wanted to make this automated cattle workflow first, and you can still have the other workflow if you want. If you want, you can still get that container that you worked with last week and that has some little customizations. But we wanted to make the automated workflow the default and easiest to use. All right. So that was our first kind of foreground containers. Now we're going to start a few background containers. First, non-interactive containers first. So I'm going to do docker run jpetazzo/clock. So when I do that, just like with BusyBox, it's telling me, well, I don't know what is jpetazzo/clock, so I'm connecting to the library and I'm downloading the image for jpetazzo/clock, And then this is a containerized clock. So every second it shows the date on standard output, and it shows it in, that's GMT. So that's why it's not 4 p.m. obviously, but in GMT it's 4 p.m. And it repeats that forever, every second. All right, I interrupt it with Control C. And now I'm going to run that container in the background. So to run a container in the background, I just add the -d flag here. -d stands for detached or demonize. And when I do that, I get like this long hex ID on the output. A little bit like if I do sleep 10 ampersand, then I get a job ID and a process ID. So well, when you do docker run -d, you get a container ID on the output. That's pretty much the same kind of concept. Okay, so now how do I check running containers? A lot of the Docker commands are kind of copied from the Unix commands so that it's easier to remember. So to check running containers, it's docker ps. And so that will tell me that I have a container jpetazzo/clock. This is the ID of the container, which is exactly the string that we are seeing here, but like only the first characters. Then it tells me that I created it 40 seconds ago, and it's been up for 40 seconds. Okay. Now I can start additional copies of this container very easily. So I can do the same command again and again, like docker run -d jpetazzo/clock. And now if I do docker ps, I see that I have those 3 containers, so one that has been running for about a minute and the other one's just for a few seconds. So far, so good. There are a few extra flags for docker ps. So first, there is docker ps-l, like last, to only show the last container that was started. And there is docker ps-q to only see the IDs of the containers. And you can combine them to do, for instance, docker ps-lq, which means show me only the ID and only of the last container that has been started. This is extremely useful in scripting scenarios when you want to start a container and then you want to do something on that container. So how do we see the output of this container? Well, we are going to use the docker logs command. So I can do docker logs and then I put the ID of the container. So I could like copy paste the ID from here, or if I'm so lazy that I can't even use the mouse, I can just type the first characters of the ID. That works just fine. Like for instance, if the ID is 29DE, etc., 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 I can just type 29D, and as long as it's the only container whose ID starts with 29D, then I'll be fine. So I do that, and it shows me the full logs of this container. If I do this repeatedly, you can see like on the last few lines, the timestamp increases over time because that container is still running and it's still outputting the time every second. Now, what if I want to continue to see those logs? Like I want the equivalent of tail-f, you know, when you see the last lines of a log file and you continue to see new log lines. Well, you just put docker logs -f, like follow, and now this remains attached to my container, and I can see the output of the container live. So imagine, fast forward a couple of hours, this container is still running, I do docker logs, I will get 7,200 lines of output if this has been running for 2 hours. That's a lot of lines of output. So we would like the equivalent of the tail option. So of course, I could do docker logs pipe tail, but that wouldn't be super efficient because that would basically pull all the logs from the container and then pipe them through tail. Instead, I can just ask to the docker logs command to show me the last few lines of logs, like the last 10 lines. Like, whoops, sorry, that's -t. What? Right, --tail, sorry. --tail 10, --follow. and the ID of the container. So that will show me the last lines of log. So it's a very common pattern to do a command like that, or even I'm personally like --tail1. So that shows you like the last line of logs, and then it continues to show the logs of the container. All right. Okay, so we have 3 containers up and running. How do we stop them now? We have a couple of commands for that, docker kill and docker stop. And in kind of in the classic Unix tradition, the stop command means that you're being nice and you're asking politely to the container to stop. And docker kill means stop immediately right away. So when you do docker stop, what happens is that the term signal gets sent to the container. And by sent to the container, I mean sent to the first process in the container. And after, by default, 10 seconds, Docker will check again on the container. And if the container is still running, then it will kill it. So it's a little bit the same thing when you do like etc initd some service stop. It will typically try to stop like nicely, gracefully. And if after some timeout the thing is still running, it will kill it. Otherwise, when you want to shut down or reboot the machine, it could take forever because one service is refusing to stop. So I'm going to do docker stop to 9d. And as you can see, my container is not well behaved. It completely ignores the term signal. It's like, oh, you're asking me to terminate. Yeah, whatever. I'm going to continue to print the clock every second. And after 10 seconds, then Docker comes back and say, okay, then I'm sending you the kill signal, and you can't intercept or do anything to the kill signal, and it stops it. If I do docker ps, I see that I only have 2 containers left, and I'm going to do docker kill, so A8B and D24D. So I put the ID of my containers. So you can see that for the stop, kill, and a lot of other commands, you can put multiple IDs to act on a bunch of containers. And so that's exactly what I did here to terminate those containers. And now docker ps shows me 0 container running. So are those containers really gone? What can I do with them? Can I still see them? Yes, I can with docker ps-a, like all, including stop containers. So I have a kind of dilemma here. Either I show it with a big font and then it looks terrible because the lines are broken, or I unzoom and then it looks less terrible because the columns are respected, but then it's so small that you can't read. So I'm going to kind of switch between that a few times. But in the docker ps-a output, we can see all the containers that we ran since the beginning. So the 2 BusyBox containers, then 3 Ubuntu containers, then 4 clock containers. So the first one, which was on the foreground, then the 3 ones in the background. All the containers are here. So what can we do with them? Can we restart one of those containers? Can we reuse it? Yep, we can. So first, you can see sometimes, like in some documentation, some strong difference between background and foreground container. This is completely artificial. From Docker's standpoint, there are containers and that's it. Well, there are running containers and there are stopped containers, but Docker doesn't have the notion of foreground and background container. It has the notion of, oh, something is kind of plugged into that container and is currently streaming the output of the container, but it doesn't have the notion of this container is in the background or the foreground. It's a little bit like if you think about a rack with servers in the rack, and you have servers with keyboard and screen plugged and servers without the keyboard and screen. And so in 99% of the scenarios, it doesn't matter at all, and it will not change a single thing whether there is a keyboard and screen plugged into the server or somebody attached to the container. I say 99% because if you really want to be picky, you can detect if a screen is connected to a computer thanks to EDID, and likewise, in a container, you can detect if there is something connected to the input of the container by using VT escape sequences to probe the size of the terminal. And if that works, you can say, aha, there is probably something connected to the terminal, probably. So there is no strong difference between background and foreground container. If you are running a container in the foreground, you can detach from it. So for instance, I'm going to do docker run -ti Ubuntu. And in that container, I'm going to run top. And then I'm going to hit the detach sequence with, by default, is Control-P, Control-Q. That gets me back to my Docker machine. If I do Docker PS, I see that this Ubuntu container is running. And I can do Docker attach on the container. And that gets me back in the container. So if I want, I can detach from my containers and reattach. This probably should not be used as a substitute for screen and tmux, but if you're so inclined, you can. Now, what about the Ubuntu container where I installed Figlet earlier? I believe it was that one. That's the second Ubuntu container that I started. So I'm going to try to restart it and then attach to it. So I'm going to do docker start on this container ID. So now it shows up in Docker PS. And then docker attach on this container ID. And I'm going to try Figlet High, and that works. So I was able to restart my old container, and it's exactly in the state I left it. So if I want, I can have the VM workflow I was used to. One thing is that so first, if you want to see the output of a container, you might be tempted to do docker attach. Do not. If you want to see the output of a container, use Docker logs. Because when you do Docker logs, so you see the logs of the container, okay, that's fine. Then you do Control-C because you're done with checking those logs. If you do Docker attach and you do Control-C, you will be sending Control-C to the container and you will be stopping it. So it's probably not what you want. So if you want to see the logs of the container, then use Docker logs. Don't use Docker attach. The actual use cases of Docker attach are pretty rare. When you attach to a container that has an REPL, so read, eval, print loop, including a shell, you will see this kind of weird thing. I'm going to show it again. So I'm going to start the container, then I attach to it. And when you do attach, it's like, hey, it doesn't work. I don't see anything here. It works. The container is running. You're attached to it, and everything works fine. But the container doesn't know that somebody just attached to it, so it doesn't know that it's supposed to display the shell prompt. If you want to see the shell prompt, you should hit Enter or Control-L, or you can just type a command and that will work. Okay. Yes? How do we deal with things like the out-of-memory killer? Is there a watchdog to restart container? Okay, so the out-of-memory killer is on a per container basis. So we have the out-of-memory killer system-wide, which, like, when your system goes out of memory, will more or less randomly kill processes. With containers, by default, if you don't do anything, it will work exactly the same way. So system-wide, like some random process will be killed. And yes, you can end up with the scenario where this container is using too much memory and this other container is being killed for it. But you can also set memory limits in your containers. And in that case, that memory limit will be enforced inside the container. And in that case, when that container goes out of memory, then that container will be in trouble for going out of memory. And then you have multiple options. By default, Docker will not automatically restart containers, but you can give it an extra flag when you do Docker run. You can do -- restart equal always, and there are a few other options like restart on error, and in that case, the container will be restarted automatically. You will also get notifications. There is an events API that lets you get like a real-time stream of events about what's going on. And in that case, you will get info about, oh, that container went out of memory and was killed. All right, so are there other questions before we move to the next chapter, which is about Docker images? Yes?
Forgot how we ended up with the bracket IP-172 label at the beginning.
How do I get like this fancy prompt?
Yeah, why is there the IP label?
Oh, why is there the IP label here? Oh, so this is just a custom prompt that we have in those VMs. It shows us like so it's PS1, this. So it gives us like the internal, so this is the host name of the VM, which by default is IP dash the internal EC2 address. This is a Docker prompt info, which this morning will not be used at all, but this afternoon, for those who will do the advanced workshop, when we will use the Docker API to talk to different machines, this will turn into the name of the machine that we're talking to. And this tells us that we are the user Docker and that the IP address of the machine is this. It's just a custom prompt to make our life a little bit easier, but that's it. It's not Docker specific. Yeah. What was the sequence to detach? By default, it's Control-P, Control-Q. And if you don't like that, you can change it. The details explaining how to change it are either in the documentation or in the PDF, like the full PDF of the slides, like the specifics of how to change the detach command. I thought that this maybe is not in the core set of things you need to know to use Docker, so it's only in the more advanced materials. All right, let's move on with Docker images. So here I want to explain like the difference between an image and a container and talk about the notion of layers and talk about image namespaces and then how to search for images and see which images are available locally on the machine, but also in the remote libraries. So technically, an image is a collection of files and some metadata. Those files are nothing else than the root file system of the container. If you've done some sysadmin things, if you want to create like a base image, you could make a tarball of the full file system of a server, and then you could import that into Docker. That would work. That's how you create base images. So its image is collection of files and also some metadata. That's one of the big differences between just like a tarball and a container image, because the container image also says, oh, so the default program to execute in this container is, for instance, bash. In the case of the Ubuntu image, I do docker run Ubuntu, and it knows, oh, you want to get a shell. If I do docker run nginx, it's going to start the nginx process, and so on and so on. There are also some other bits of metadata that we will learn more about later. Then those images are broken down into layers. Each layer can add, change, or remove files and metadata. So instead of being this big block and okay, that's an image and that period, the image can be broken down into independent layers that can be shared and reused and updated independently. So for instance, let's say, I should have put like a Python example here, but let's say you have this Java application. So you say, I have like my base CentOS distro. On top of that, I install the GRE, so the Java environment. Then I install Tomcat, which is this server to run Java things. Then I have the dependencies for my application, like all the libraries I need. Then I have the application itself, and then I have some configuration files for my application. This means that when I update my application, instead of rebuilding the whole thing, I can only rebuild my application and the configuration that goes with it. If I want to do a big Java update, then I have to kind of scrap all those layers and restart from that point and rebuild from there. But basically, when I'm just doing small updates into a small part of my application, I don't have to rebuild everything. I only have to rebuild the layers that have changed. And so those layers can be reused between images. Like if I have another Java application, I can reuse those two base layers, which are most likely the biggest ones. If I have multiple deployments of the same application, but with just different configuration files, I can reuse all those layers and just change that tiny configuration layer. Same thing when I need to move layers around. Like the first time I will push those layers somewhere to share my application with someone, I will push everything, and that's going to be a little bit slow. But when I'm doing an update to my application, I will only push what has changed, and that will be much faster. So we end up saving disk space, bandwidth, and also in some scenarios memory use, because the memory of those layers can be reused between containers. So now what's the difference between a container and an image? An image is just a bunch of files and data. It's kind of something living on disk. A container is a bunch of processes running in a read-write instance of this image. Images are read-only. You cannot change an image. Well, you can if you go into the file system and do stuff, but you should not do that because you're most likely to break things. The container will be the read-write version of that, and so you create multiple containers from a given image. So we can see that as stencils, or something that I prefer because it comes from development. You can think of images as classes. Layers are a little bit like inheritance. When you create a new class inheriting an existing class, so it can add and change methods. The same way, well, you can create a new image on top of another image by adding a layer. And then containers are like instances of a class. So if images are read-only, how do we change them? Like, how do I install Figlet, for instance, in my image? Well, you don't change an image. There is no way, except, again, by going into the file system and breaking things. So the way we create new images is by creating a container from an existing image. So now we have a container. We can change things in that container because it's read-write. We make changes, and when we are done, we are turning this container into a new image. So I have an image, create a container, make changes, and freeze that container into an image. And that's how I get my new image. So the only way to create an image is by freezing a container. But the only way to create a container is by instantiating an image. So I have a kind of chicken and egg problem, like what comes first, the container or the image. So there are a few ways to break that recursion issue. First, there is a special empty image called Scratch, which contains nothing. And it's called Scratch because we will see in the Dockerfile recipes, the first line is from, and it indicates the base image that we're using. So in that case, you're using from scratch because you're building from scratch. Then we have the Docker import command. Like you can make a tarball of an existing server and say, okay, I want to create an image out of that. So that gives you a base image. But most likely, the way you will build images is with the docker commit and docker build commands. So docker commit is the command to freeze an existing container into a new image, and docker build will take a Docker file, a recipe to build a container, and it will just apply the steps and give you your new image. And we're going to use that in just a minute. So there are different namespaces for images. We already saw two of them. The first containers that we started were like Docker run BusyBox and Docker run Ubuntu. And then we did like Docker run jpetazzo/clock. Those are two different namespaces. The root namespace, so when you just have like the name of an image, that's for official images. So those contain like distro images, a bunch of components. We'll have like MySQL, Postgres, Redis, Mongo, and much more. And also language stacks like Python, Java, Ruby, Node, and so on and so on. Then you have the user namespace where basically anybody can put whatever they want in there. You just like create an account at the Docker Hub, and if your username is jpetazzo, then all your images will be jpetazzo/whatever you want. But then if you don't want to use the Docker Hub, that's fine. You can also host your own library of images. And in that case, the reference to the images will be the host name, optionally the port, / and some image name. So in that case, I'm referring to the WordPress image hosted on localhost port 5000. So this assumes that I have a registry, so a collection of images, a server running on my local machine. So how do we store those images? Images can be stored in two places. They can be locally, like in a Docker engine, like ready to run. So in that case, they are in a special format that makes them ready to be started really quickly. But they can also be in a library server, what we call a registry. And to move them between both, we have two, let's say 3 commands. There is docker pull and docker push to explicitly download and upload, but there is also docker run, because when you do docker run, if you don't have the image locally, it will try to fetch it from a remote server. So if I want to see the images I have locally, I can do docker images. And in that case, we have the images that we run. So we have Ubuntu, we have BusyBox, we have jpetazzo/clock, and a bunch of other images that had been pre-pulled when we deployed those VMs this morning. If you do that on a freshly new installed Docker system, Docker images should show nothing. As long as you haven't run any container, Docker images will be empty. Then you can also search for images in libraries with Docker search. So for instance, what if I want to do some Django stuff? So I can do Docker search Django. And in that case, I'm pretty happy because it tells me that you can see like the first line, there is an image named Django. So that's an official image. And then I have a bunch of other images that have been contributed by other people. Let's see, for instance, Docker search, maybe like if I want to run salary workers. There is also an official image. All right, so I'm going to use the example I have in the slide, which is Zookeeper. And in the case of Zookeeper, I don't have an official image. So in that case, I'm like, okay, what should I use? Usually the official image will be the kind of best thing to use. But if there is no official image, then you can use the number of stars as an indication of the kind of popularity of the image. Stars are like Facebook likes, but for images. It gives you a kind of approximate indication of how popular and used the image is. And then if you want to get more details, you can go to the Docker Hub. And on the Docker Hub, you also have a search interface. And for instance, like if I want to see, okay, how do I use this Django image? Like, can I have some extra details on that? And maybe I can do that. Or I can check on one of my own images here. And so I get more details on the image, like where it comes from, what's the Docker file that we used to build it, and so on and so on. So all those informations are not visible from the command line. Like the command line only gives you like super basic info, but you can get more details by going to the website. And if you are running your own registry, then it's kind of on you to provide this kind of information. There was a question there.
You just answered it.
Oh, okay, cool. All right.
Sorry, did you say that you actually provide that information, so on that Docker Hub?
So yeah, the Docker Hub has like the component to host images, which is a little bit like a glorified FTP server if we were to really simplify things. And on top of that, it has a bunch of other things like the nice fancy website with the description and the showing you the Docker file. There is an automated build platform. There is a lot of extra features. So if you're running your own registry, you will just have like the basic like file hosting component, and all the other features have to be added on top. The search will work, like the open source registry supports like search operations, but if you want the fancy web dashboard, you have to slap that on top of it.
But so as a consumer of these images, how can you trust that images don't have malicious content?
As a consumer of those images, how can I trust those images? So here, it's the same kind of workflow as with packages. Like when you get packages coming from your distro, you like, okay, I trust the Debian maintainers or CentOS maintainers or the Gentoo community to kind of cater for this and watch for this. So here's the same thing. If you are using an official image, I could go into the detail explaining how this works, but it's a little bit like for distros, there is a mechanism to vet new official images and maintain them. Now, if you're getting a completely like random image from someone, like if I try to run this image, like I don't know who that is. So absolutely, in that case, it's exactly like getting something from Launchpad or downloading an RPM or deb from who knows where and trying to run it. It could work or it could be very risky. There are some restrictions on the damage that a container can do. Like if I do Docker run something, like as of now, there are no known ways to break out of a container. But maybe in 2 weeks, it's like, oh, security issue, and now if you do Docker run evil thing, that could break out of the system. This is a frequently asked question, like, well, this seems risky. Like, how should I trust those container images? And in fact, I'm extremely happy that we are starting to think about this, because many people are installing stuff without thinking about it. Like even if you do pip install something, if you pip install something that comes from you don't know where, there is no guarantee that this will not break your system and ship your code to some third party. Same thing with NPM, with Gem, the Ruby package manager. Every package manager has this issue. And with containers, somehow people started to be more aware of it, because I think it's because now we realize that it's shipping a full system. And so there is the perceived notion that it can do more damage. But in fact, it's the same thing with existing package managers. So here, yes?
Excuse me. So if a image is labeled like official in the root namespace, does that mean that they are offered by the official maintainer, for example, for Ubuntu?
So if an image is official, does it mean that it's maintained by official maintainers, like for instance for Ubuntu? So it depends. In that case, you have to check like per image. For instance, for Ubuntu, CentOS, they are maintained by the respective companies, so Canonical, Red Hat. To give you a short anecdote on how this happened, initially there were like maybe 10 official images, like the distros mainly, and Docker was like the maintainers, so mostly people from Docker Inc. and a few other external contributors were maintaining that. And someday, Canonical showed up and say, okay, so at first we didn't like care about Docker because it was small and nobody cared really, but now there are people starting to use it, and there are people doing Docker run Ubuntu, and they get a version of Ubuntu which is not exactly the official Ubuntu image because it was slightly adapted for containers. And so they basically, Canonical wanted to control and maintain the Ubuntu official image. And we said, hell yeah, because that's less work for us. And also it guarantees that it's closer to the Ubuntu version that you want in containers. So for the vast majority of official images now are maintained by either the company backing the project or by the official maintainers or by other contributors. Like there sometimes the company or the community behind project X doesn't want to maintain a Docker image because they don't care, but there will be someone from the community saying, hey, we would really love to have a Docker image for that, and they do it. Or sometimes it just takes time. Like Console, which is a key value stored like by HashiCorp, for a long time they didn't have an official image, but they cared, but it's just that they wanted to take the time to make it right. And they made it last month, I think, and it works great. So, but generally when there is an official image, it's like, it's A-okay, because either it was done by the company behind it or by Docker contributors. Yeah. And you can check who did it, like with the maintainers thing, like I think if I do Docker inspect Ubuntu, I will get that somewhere. There should be a maintainer information somewhere, maybe. I don't see it here, but author maybe. Well, that will, or otherwise it will be on the Docker Hub in the maintainer flag. Yeah. All right, where was I? Okay, Docker search. So how do we move images around? Well, we have Docker pull, Docker push, and the implicit Docker run, which will automatically pull the image if needed. When you do Docker pull, it will check if you have the latest version of the image. So for instance, if I do Docker pull Ubuntu, I already have Ubuntu, but this will check, okay, what's the last version of Ubuntu, and then it says already exists, so it doesn't re-download it when it's already what I had. If I want, I can get specific versions. For instance, I can do, let's do a Python example. I can do Docker run Python. So if I do Docker run Python, this will like download the Python image. And then by default, instead of starting a shell, it should start the Python interpreter. And I think by default, it defaults to Python 3.
So each of those are layers. Is there any way to see what the different dependencies for images before you download it?
Is there a way to see the different dependencies of each layer before you download it? So in that case, we have multiple layers, but they are not exactly dependencies in the sense that I can't really see a dependency tree like I would see for packages. Like, because for packages, it's like this package depends from this and this and this package, while for layers, it's a linear stack of things. It's like this is built on top of that, on top of that, on top of that. So if I want, I can do it's Docker history Python, and that shows me the layers. And so in that case, this is an intermediate size thing. I can see that at first in the Python image, it's adding like a base layer that is like the bootstrap thing, so it's imported directly into the image. Then this is probably like, this is the stuff, I think, from the base Debian image. Then it's removing the existing Python. Then it's setting a bunch of environment variables. And then it's getting Python from somewhere to have exactly the version we want. And at the end, it's say, okay, when by default, we want to start the Python interpreter. So if I do docker run -ti Python, I get Python 3.5.1. Now, if I want a specific version, I can do like colon and the version I want. Like, let's say I want Python 2.7. I do docker run -ti Python :2.7. It's going to download an image with Python 2.7. And now I get 2.7.11. I might even be able to get like exact versions. Like, let's say, oh, I want 2.7.10. Can I do that? Yes. And there is a kind of almost semantic versioning. Like, if I want, I can do docker run -ti Python :2, because I just know I have some code that is not updated to Python 3 yet. So, but I don't really care about which version of Python 2 I get. I just want the latest Python 2. So I could do docker run Python :2. And same thing for distros. If I want, I can do docker run -ti Ubuntu :1204 if I want this older version of Ubuntu, because I have some binaries that only run on this older version of Ubuntu. So we have those tags. By default, if I don't give the tag, like if I just do docker run Python or docker run Ubuntu, what do I get? I get Python :latest and Ubuntu :latest. So it's just like, like on Git, it's master, like the default branch, and on Mercurial, it's default, I think. So it's just like the default tag to use. So when should we use a tag and when should we not? The general idea is that when you are prototyping and experimenting, don't put a tag. You can just do like docker run Python and you get like the latest version of Python, or docker run MySQL, you get the MySQL server. Now, once you are done experimenting and you are scripting things for automation and repeatability, then you want to pin to a specific version so that you can be 100% sure that if you put those scripts in the closet and get them out like 6 months, 2 years later, they will still work the same way. Because in 2 years, if I do Docker run Ubuntu or Docker run Python, I will get a different version of Ubuntu or Python. However, if I do Docker run Ubuntu 1604 or Docker run Python 3.5, then I will get exactly that same version, and I will be sure that everything will work exactly as it did 6 months or 2 years ago. All right, so that was all about images and layers, and let's see how we're doing on timing. 10:20, so I think we are supposed to get like the coffee and something break, and then we will see how to build images. Let's gather again at 10:40, maybe. So before we resume, first, little kind of quick check on pace. Who thinks that we are going too fast? Nobody? Well, a little bit. Too slow? Just the right speed? Okay, great. So we're going to try to maintain kind of the same speed. I might like maybe squeeze out one chapter or something to make sure we can cover everything, but we're doing good. All right. So we saw how to install something in a container, but now what if we want like that little Figlet tool to be installed by default? What if I want to have a container that comes pre-installed with Figlet? And we're using Figlet in that case to keep something super simple because I want something that you can transpose to the field of your choice, and specifically at the end of this whole section, I will show a Docker file showing like what it's like to run a Python app in a container. But for the examples here, we will use that little Figlet program to kind of focus on something really small and simple. So how do we make our own images? So we're going to see 3 commands. Well, we're going to see 2 methods, the manual method and then the automated method. In the manual method, we're going to see 3 commands. So there is docker commit, docker tag, and docker diff. All right, so we're going to start with the Ubuntu base image and build on top of that. So I'm going to start an Ubuntu container, so docker run -ti Ubuntu. I'm going to do apt-get update, just like earlier. And then apt-get install Figlet. If I were installing a real application, here I would do more stuff. Maybe I would git clone some repo and install dependencies and build some things and create configuration files and generate whatevers and do the whole install process. And once I'm confident that everything works fine, it's like, okay, I'm happy with the result, then I can exit the container. And then I can view, okay, what did I do in this container? I can do docker diff. I do docker diff and I put the container ID. So in that case, again, either I copy paste the ID from here, or I'm so lazy that I won't even touch the mouse and I just type the first characters of the ID. And this outputs like a big list of the files that have been added, changed, or removed between the base image and my container. So I can review that, and in that case, that's basically all the files that have been installed by Figlet. In the case of something that's been installed with your package manager, that's not very useful. But you know when you have this vendor-provided binary thing, like there is install.sh and it downloads something from the internet and you don't know exactly what it's doing, but you would like to know, in that case, Docker diff is really useful because it will show you exactly what was changed in the container. So, okay, I reviewed my change, and now I want to create an image out of that. So I do docker commit, and I put the ID of the container. And it's saying, okay, there is your new image, and the unique identifier for the image is like SHA256 : and this very long image ID. Now I can run this image. I do docker run -ti, and I put the image ID, so, or just the first few characters, because once again I'm lazy, so 77CE3. And I get a shell in a new container, and that container has Figlet. If I do Figlet is installed, then it shows me that Figlet is installed indeed. So that's how I can manually create a new container. So that's nice, but doing docker run on some very long, obscure image ID is not so nice. So what I want to do is I want to be able to do docker run Figlet. So I'm going to tag this image to give it a nice name. So I do docker tag the image ID, so 77CE Figlet. And now I can do docker run -ti Figlet, and it runs the same image. Great. I can even combine commit and tag. So by doing docker commit, the container ID, and the name I want to give to the resulting image. So far, so good. So that works, and there are some scenarios where you want to use that, like typically when you have those install instructions and they have some interactive steps, either because it says, and now you have to accept the license, and now you have to do some manual steps, and in that case, yeah, do that. Do docker run with your favorite distro, install everything, and once you're done, you commit. But the problem with that approach is that each time you want to rebuild, you have to repeat all those steps. Or if you want to rebuild with a different distro, like here I used Ubuntu. I don't know what version of Ubuntu that got me. Maybe, I think it's 16.04. But what if suddenly it's like, oh, we need the same image, but for the previous Ubuntu, like 14.04, or even like 12.04, or we need that on Debian or something else. I don't want to go over all those steps manually each time. I want something more automated and streamlined, and that's where we will use Docker files. So a Docker file, so it's Docker file with an uppercase D. We just follow the convention of like, makefile, uppercase M, gem file, uppercase G, vagrant file, uppercase V, and so on and so on. So a Docker file is uppercase D. And a Docker file is a recipe describing how to build a container image. And then there is a Docker command, docker build, that will take that recipe and execute it step by step and create a new image for you. So we are going to build, to write a recipe, to write a Docker file to build a Figlet image. So the first thing that we are going to do is to create an empty directory for our build. And I will explain in a few minutes why we have to create an empty directory for that. So make directory my image. Then I go to that directory. All right. And then I create my Docker file. So I'm going to use VI, but you can use whatever editor you want. So if you prefer Emacs or whatever, feel free to use it, install it. Those VMs are yours, and they will be up until tonight. So if you want to install something on them, that's totally cool with me. All right, so what should we put in the Docker file? So our first Docker file will be really simple. It will be 3 lines from Ubuntu, then run apt-get update, run apt-get install Figlet. So the first line indicates the starting point, and you have to put that. Like a Docker file has to start with from something. So in that case, from Ubuntu. Then run, and each run line indicates something that I want to execute in my container. So run apt-get update, run apt-get install figlet. And I often say kind of, I joke about the fact that it's super easy to write a Docker file, because if you know how to write a shell script, you just take your shell script and you put run in front of each line, from on the top, and that's a Docker file. And that's almost correct. But the general idea is that the Docker files should be really easy to write. All right, so that's my first Docker file. Is run case sensitive? It's not. You can put lowercase, but there is a kind of convention that those things are put in uppercase. It's a fairly good question. I think it just, it's like some traditions. It started like somebody said, okay, let's put uppercase thing because it sounds like imperative, and also it stands out a little bit more, but it could be lowercase. All right, so this is my Docker file. Now, how do I build it? Well, I Docker build. So you do Docker build -t to indicate the tag that you want to have for the resulting image. So in that case, I want figlet. And then you indicate the directory that contains the Docker file. So in that case, it's dot. I do that. And so in the output, so it's going to do the apt-get update. Now it's doing apt-get install, and that's it. My container is built. If we review, yes?
Your naming convention, the my image can be any name, but the Docker file has to be called Docker file.
So in the naming convention, you can name the directory whatever you want in that case, yeah, but the Docker file has to be called Docker file, yeah. Well, there is an option to indicate the Docker file to use, like if you want to name it something else, you can, and then you do Docker build -f, like my other Docker file. But by default, it will be Docker file like that, yeah. So if we look like in the output of the build command, the first thing that we see is sending build context to Docker daemon, like the first line, and it went kind of quickly, but I want to go back on that. So sending build context means that the Docker CLI is kind of wrapping the build context, so the directory that we indicate to the CLI, so dot, it's taking the current directory, making an archive of that, and sending it to the Docker engine. Why is it doing that? Because remember, I said that each time you do something with the Docker engine, it goes over a REST API. So if I'm telling to the Docker engine, hey, build from the current directory, the Docker engine has no way to access my current directory. If it's local, then yeah, the Docker engine could do some really weird tricks to find out where is the client calling me and what's its current directory and get the files from there. But if I'm talking to a remote Docker engine, there is no way for that remote Docker engine to access my local files, which is why when you do Docker build, it wraps up the build context, so the directory that you pass to the build, and it sends the whole build context to the engine so that the engine can get those files, which is why we created a separate directory instead of just putting the Docker file in the home directory, because then you would do Docker build dot in your home directory, and it would send your whole home directory to the Docker engine, which is probably not what you want. In that case, that would be fine because it's a completely new VM and the home directory is empty. Now, if I do that on my Linux machine, I probably have 10 gigs of crap in my home directory, so I'm going to send 10 gigs to the engine each time I build. Not a good idea. So we send the directory to the engine, and basically then the engine receives that bundle. So it's, I think internally it's a tar file, but it opens it. It's like, okay, there is a Docker file, so I'm going to execute that. The first line is from Ubuntu, so we need to get the Ubuntu image. We already have it, great. Otherwise, it would pull it automatically. And then you say, oh, you want me to run apt-get update? Fine, let's do that. So it executes apt-get update, and then it takes a snapshot of the resulting container. Then it's like, okay, what do you want to do now? Apt-get install? Fine, let's do that. And at the end, you get your build. Now what happens if I do the build again? Like I execute exactly the same command. This time it's instant, because each time that Docker goes over a run command, first it checks into the cache, have I done that before? And in that case, the answer is yes. Right? So it's like you ask me to do apt-get update on top of Ubuntu. Yep, we just did that 1 minute ago, so I can use the resulting snapshot instead of doing apt-get update again. Then you ask me to do apt-get install figlet on top of apt-get update, on top of Ubuntu. Did we do that before? Yep, we did, and so it's using the result. Now if I change the slightest thing in my Docker file, like let's say that here I'm adding one extra space after apt-get install, and I say, okay, Docker, build that again. It will skip the apt-get update because, okay, you're asking me the same command. However, when it goes to the apt-get install space figlet, it's like, we haven't done that before. I mean, yeah, we've done apt-get install space figlet, but Docker doesn't try to be smart. It doesn't try to be like, oh, 2 spaces are just like 1 space, so I'm going to use the cache thing. Because maybe there are some cases where 2 spaces and 1 space are not the same thing. Or in the example here, if you're doing apt-get install this and that, Docker has no way to know that it's different from apt-get install that and this. Like, is it different? Is it the same? It depends. With apt-get, you can switch the order and it will work, but with other commands, the order of parameters will matter, and so Docker doesn't try to be overly smart and to infer that it's the same thing. So that's great because this caching system means that rebuilds will be super fast. In that case, it doesn't seem like a big deal because apt-get update, apt-get install, a single package, that's super fast. But if we're doing Django stuff on a fairly big stack and you have a requirements.txt file that has like 20 lines of dependencies, installing all of that could take a couple of minutes, and you don't want to spend those 2 minutes each time you rebuild your container image. So thanks to the caching mechanism, rebuilds will typically be just a couple of seconds. Now, what if you're like, okay, but if I take this machine, set it aside for 6 months, and I come back and I build again? Normally, in 6 months, the packages have changed. So I don't want to use the cache. I want to get fresh packages. How do I do that? Well, you can use the -- no cache option, which tells to the Docker build system, ignore the cache for that build and re-execute everything, re-download the package lists from the mirrors and so on and so on. All right. So if I want, I can have a look at the layers of my figlet image. I can do Docker history figlet, and I know that maybe this is not super readable from the back of the room, but you can do Docker history and see on your screen. But what I want to show is the layers composing my figlet image. So first, I have those 1, 2, 3, 4, 5 layers here, which are the base Ubuntu image. And so in this base Ubuntu image, I'm adding a bunch of files. So it's like the base root file system. Then I'm doing a little bit of cleanup in the image, and then here I'm defining in the Ubuntu image, I want the default command to be bash. And those 2 layers here are the layers added by my Docker file. And I can see the apt-get update layer and apt-get install figlet layer. All right, and you can see like the base image, the Ubuntu image was created 2 days ago, contrast with the 2 other layers, which were created 6 minutes and 2 minutes ago. Okay. So if we look in this output, sorry, I zoomed a little bit too fast, but we can see here I said apt-get update, apt-get install figlet, and instead I see sh-c blah, blah, blah. Why? Because you can't really execute apt-get update. What you execute, in fact, is you have to break down the command and the parameters. And so Docker does that by taking the string, like the thing after the run command, and passing that to a shell, and it tells it, okay, parse that and execute it, which is why I see sh-c apt-get update. I can also, in my Docker file, use a slightly different syntax that we call the JSON syntax. And in that case, instead of putting a string here, you put a JSON list, which happens to also be the format of a Python list. So it's like square brackets, and then each parameter is between double quotes with commas. And then I build that. And so when I build that, instead of taking the string and passing that to a shell for expansion and breakdown and everything, it directly executes apt-get install figlet. And now if I look into the output of Docker history, you can still see sh-c apt-get update. However, for apt-get install figlet, now it's executed directly without sh-c. So when do we want to use the string syntax and when do we want to use the JSON syntax? For run commands, generally, we just want to use the shell syntax, the string syntax, because the JSON syntax doesn't have really an upside. But the idea is that when you put the shell syntax, the string version, then, I mean, I'm going to illustrate with a Docker file so that, like this syntax will let you expand environment variables. Like if you put something like $foo, this will be expanded. Same thing for home directories and so on and so on. However, when you put this syntax, then it will be directly executed without any substitution, replacement, expansion whatsoever. Okay. So so now we know how to build an image, and we have like the really basic stuff to build an image. But when I run my figlet image, I still get a shell in this image. And in this chapter, I want to show how we can change the default command to run in the container. When I want to do Docker run figlet, I want to automatically execute figlet basically, which I can already do if I do like Docker run figlet, and then I say what I want to run. I say like figlet hello. But basically what I want is to be able to do Docker run figlet and see directly hello. So for that, we are going to define the default command. And in the Docker file, we do that with the cmd instruction. So I'm going to edit my Docker file, and I'm going to put cmd figlet -f script. It's to use a fancy font for figlet. And hello will be my default message. So I do that in my file. Then I build again. You can see that the build is super fast in that case because the expensive long steps like apt-get update and apt-get install don't need to be executed again. And now I do Docker run figlet, and it executes the default command. So now instead of getting a shell, it executes that. If I want to revert to the previous thing, if I say, okay, but I really want a shell in that container, fine, let's do Docker run -ti figlet bash, and now I get a shell. I get a shell, and you get a shell, and everybody gets a shell. Okay. Now I want my container image to be a little bit like a binary, like a program to which I can give arguments. I want to be able to do Docker run figlet some message, and I want it to display the message. For that, I'm going to use another keyword. I'm going to use entry point. Entry point lets you define like a base command, and all the parameters that you will add after Docker run will be added after this base command. So for instance here, I put entry point figlet -f script, and if I do Docker run blah blah blah, it will execute figlet -f script blah blah blah. So let's do that. So entry point, and the entry point has to be in JSON syntax. I will explain why in just a minute. So the entry point has to be in JSON syntax, because if it's in shell syntax, then what happens is that when Docker starts the container, so if I put like a entry point figlet-f script, then Docker will start sh-c figlet-f script. Oh, let me show that like that. sh-c figlet-f script, and then the other parameters. And so when you do that, then the other parameters are just discarded by the shell. So they would just be dropped, and you would not be able to pass your extra parameters. So entry point has to be in JSON syntax. I rebuild my container, and now if I do docker run figlet PyCon, it's going to execute figlet-f script and the extra parameters after the docker run command. All right, now, what if I want to give a default set of parameters? So basically, I want to be able to do docker run figlet, and if I do docker run figlet, I will just see hello. But if I do docker run figlet some other message, then I will see some other message instead of hello. In that case, we combine entry point and CMD. Like I say, the default message will be hello. I build. I rerun figlet. So if I don't give parameters, it will do figlet-f script hello. But if I give parameters, then it will do figlet-f script the other parameters. So whatever I put here will replace CMD. The whole point of that is to have containers that they are not just like it's not just like a little thing that you can spin up by pressing the start button. You also have parameters that you can give to the container, and that lets you write containers that behave like local, like command line utilities. All right. And yeah, if you're using CMD and entry point together, the only gotcha is that you have to use JSON syntax for both in that case. Otherwise, that won't work exactly as intended. All right. Yeah, I'm sorry. Sometimes I advance forward in the demo without advancing in the slides. So then after, I have to skip like 5 or 6 slides because I went over all of that. So if we define the entry point, how can I get a shell in my container? Like I have this little figlet container and I want to get a shell in it. So docker run -ti figlet bash. That doesn't work because now if I put bash instead of executing bash, it just gives bash as parameters to figlet. So how can I override that? Well, that's really easy. I have a -- entry point parameter to override whatever the entry point is in my image, and now I get a shell in the container. This means, by the way, that if you want to prevent people from looking inside the container, you shouldn't use the entry point as a way to block them because they will be able to override it. All right, so what we saw so far, we are able to write a Docker file to package pretty much anything. Except we only have the run command for now. So like if you want to build a container for something in a GitHub repo, for instance, you would do like run git clone this, then maybe run pip install that, run this, run whatever. And each time that your repo changes, you would need to docker build -- no cache and rerun the whole build. And that would be not very convenient. So instead, we have a mechanism where instead of doing run git clone, you put your Docker file typically at the top of your repository, and when you will Docker build, in the Docker file, we will have commands to bring files inside the container image. So that's the point of the copy command. So for the example here, Well, I'm going to deviate from the slides and do a Python example. Let's take risks. So make directory my Python example. And I'm going to make a little Docker file. So, well, first a little Python program. So hello.py. And I'm going to do print hello Portland. And then I'm going to create the associated Docker file. So I'm going to do from Python, copy hello.py into slash, and then cmd python/hello.py. So from Python will give me a Python image. So it's a really bare bones distro that has Python, easy install, pip, the usual suspects when you need to do Python stuff. All right, let's build that. So Docker build, let's call that hello Python from current directory. So in my case, that was super fast because earlier I pulled the Python image, but I don't remember if you also have the Python image pre-pulled, so maybe the build will be a little bit longer for you. All right, and now I can do docker run hello Python, and I see my hello Portland message. So far, so good. Now I'm going to make changes in my code. So I'm going to edit the hello.py file. And I'm going to add goodbye Portland. And I'm going to build again. So with what we saw before, it's like, oh, you didn't change the Docker file. So normally the caching system should kick in and it should just say, hey, we already have that. So it should not rebuild the image because the Docker file has not changed. But if I do that, and then I do docker run hello Python, I see that I have my goodbye Portland message. So if I look in the output of the build, right, that's what I get from deviating from the example. Here I'm going to do like run pip install. Let's install a random package, Flask, even though I don't need it. But what I want to show is that when I build this, so it will install Flask. All right, now let's make changes in my hello.py file. And hello again. And so now when I rebuild, you see that it's not downloading Flask again because it's using cache. You can see run pip install Flask using cache. But then for the copy hello.py, this time it doesn't say using cache because it was able to see, okay, you want to copy hello.py into the container, but I'm going to check that if that hello.py file has changed or not. Oh, it has changed, so I'm rebuilding the container. But if I execute docker build again, this time it's able to see, oh, hello.py has not changed, so I can use the cache. So with that, we are able to rebuild the containers only if the files have changed. So instead of just using the Docker file to assess whether it should rebuild or not, it's also checking the files that you are copying inside your container. And now if I docker run hello Python, I see my updated message here. So the idea now is instead of putting like run git clone, etc. in your Docker file, you do copy my files to some place in the container. So in that case, we did copy the file to the root directory. You probably don't want to do that. If you were to do that on an actual server, you probably have a bunch of really angry sysadmins telling you to please not put source code and builds and stuff on the root of the server. Don't do that. And if you do it again, we will revoke your server privileges. But in the specific case of containers, usually we would put that in maybe /src or /app, something like that. But even if you litter your container with files everywhere, it's less of a big deal than if you do that on an actual server. It's less of a problem because on a server, the server is most likely used by multiple people, or at least, okay, you deploy your stuff, but there might be some other admins, and when you log on a server and you do ls and you see a bunch of files on the root file system, it's generally not a good sign. In a container, it's bad, but not as bad because your app is the only thing that runs in the container. So most likely, nobody will ever SSH in the container. Well, first, generally, there will be no SSH server in the container, so that kind of solves the problem. But it's less of an issue because if you have multiple apps, there will be multiple containers. So you don't have the risk of polluting somebody else's work by putting your files in random places. It doesn't mean that you should put files in random places, but it means that the damage, if you do it, is lower. So that now, with what we saw so far, we have like really the basics to Dockerize applications. Like we can typically use a bunch of run pip install things. We could copy everything to /src. Then we could do like run pip install the /src coherence.txt, run etc. Run python /src setup POU install, etc. We could do a bunch of things like that, and you would get a container that is ready to run anywhere. There are some other instructions in Docker files that we need to know about. I'm going here to give you like the most useful ones, the ones that you most likely will need. So we covered that already. So you need like the first instruction in a Docker file has to be from, and you can use from with any kind of image that we saw before. So official images, user images, self-hosted images. There is the maintainer option that allows you to kind of put some metadata about who is maintaining the image. It's completely optional, but it gives you a way to inform who should be thanked or blamed for the image. We saw the run instruction with the two formats, like the string format and the JSON format. There was somebody asked this during the first half, like somebody asked, okay, so when I do Docker commit, does it save the state of the processes? No, it doesn't. When you build something, when you do Docker commit or when you do Docker build, it will save only the state of the file system. So if you have processes running, they are just terminated. So for instance, if you do run apt-get install Postgres, PostgreSQL -server or something like that, yes, it will install Postgres, but no, Postgres will not be started automatically in your container because, yeah, question? Does it first sync the memory buffers? Yes, it does. Yeah, so if you have some files that were kind of in flight, yeah, they will be synced correctly. So if you do, for instance, run apt-get install PostgreSQL server, yes, it will install Postgres. It will probably not start Postgres, but even if it were to start Postgres, immediately after the run command is done, so immediately after being done with apt-get install Postgres server, the Docker build is like, okay, that command it just terminated, so let's kill the container, save the state, and move to the next build step. And in the next build step, it will not start Postgres. So if you want to run, let's say, Postgres in a container, first, there is an official Postgres image, so it kind of saves you the trouble. But if you were to make your own image, if you want to start Postgres automatically, you would have to put that in CMD or entry point, not as a run command. So a trick when installing a bunch of packages is to collapse layers. So instead of doing run apt-get install this, run apt-get install that, run pip install that thing and pip install that other thing, you can put that you can use like backslashes to have multi-line continuations and use like semicolons or append to have multiple commands in a single layer. That way you're creating one layer instead of a bunch of layers. And a very common pattern is to have something like apt-get update, apt-get install a bunch of things, apt-get clean. Why do we have that? Because if you have those three things on three different run commands, then you create a first layer where you add the list of packages, then you install the packages, and then you remove the list of packages. And so you could think, oh, I cleaned up my container, so I have a kind of small, lean container, except that when you transfer the images, all the layers are transferred anyway. What I mean by that is that if you have one layer that adds a bunch of files, then a layer that removes that bunch of files, the resulting image seems to be small, but it's still just as big because all the layers have to be transferred anyway. It's a little bit like when you have a Git repo where you have a commit that had like tons of files and then another commit that removed those files. When you git clone the repo, it will still download everything because it needs the full history. So it's the same thing with Docker layers. If you have one layer that installs like a compiler because you need to build extensions, then you build the extensions, you remove the compiler thinking, oh, I'm making a small image. That doesn't work. I mean, the resulting image will work fine, but when you pull it, it will still pull the compiler because all the layers are necessary. So to avoid that, you put all the steps in one single run command. So you put run, get compiler, build extensions, remove compiler, and then you get a small image. Yes?
So that means every run command will always generate a new layer, no matter how simple it is.
This means that every single run command will generate a new layer, yes. In fact, generally speaking, every single command in a Docker file will generate a new layer. Sometimes it will be a really small layer, and sometimes a bigger one.
Okay, so in this line, you combine the different commands in one run line. Is there any limit, like how many commands I can combine?
Is there a limit on the number of commands? You can put as many commands as you want. If you want, you can put like 1,000 commands. And I mean, at some point, maybe since this is passed to sh-c, there might be a limit there, but it's not Docker related. If you really have something super long here, you probably want to put that in a script, and then you copy the script into the container, and then you execute it. That's probably a better idea. Because that way, if somebody wants to build that outside of a container, they can just run the script. And there is a limit on the number of layers, and currently it's like 127 minus a few, and it's linked to a technical limit in one of the storage systems that Docker can use. Like there is like the UFS system is limited to like 120 something layers. Other systems are not limited, but to make sure that you don't end up with an image that could run on this system and not on this, we kind of level down everybody to have the same limit on number of layers.
So in one of your earlier slides, you said that this whole Docker build is run on some remote box, right? Some remote machine.
So when we do the Docker build, it's on a remote machine. No, so in that case, so we are connected over SSH to a remote VM, and when we do Docker build, the build happens on that VM. But if we want, we could use the API, so you have an environment variable to set. You say, okay, I don't want to speak to the local Docker engine. I want to speak to this other Docker engine out there. And in that case, when you do Docker build, instead of sending the build context locally, it would send it over the network to the other machine. So another useful keyword, expose. So expose is some metadata to tell Docker, hey, in this image, there is a service running on that port or those ports. And it could be TCP or UDP. So for instance, this means This is exposing something on TCP port 80 and 443. Oh, I guess this is a web server. This line means expose port TCP 53 and UDP 53. That's probably a DNS server. You can have multiple exposed lines with multiple ports each time. And this is some info for Docker, and Docker can use it. We will see in the next chapter about networking. When you do docker run -p, it means publish those ports, and so automatically Docker will make those ports available from outside. The copy instruction, so we cover that. Copy can work on single files, but it can also work on directories. And if you put copy /, it will not copy like from the root of the file system, but from the root of the build context. Because if you try to do like copy /tmp /whatever, remember when you do Docker build, it makes an archive and it sends that archive to the Docker engine. In that archive, there is not the content of /tmp. And so this, I mean, at first it could seem like a limitation, like, hey, what if I have this file in /tmp and I want to use it in my build? Well, no, because if you do that, then the build becomes non-portable, because maybe it will work on your machine, because on your machine you have /tmp /whatever, but if you try on another machine, there will not be that file in /tmp, even if you have the same source directory. So all the files that you refer to with copy are relative to the build context. There is add, which is almost like copy, but has a few extra features. Like if you add a URL, it will download it and copy it. If you add an archive, it will automatically unpack it. But it's seldom used because generally it's just easier to run curl to get the remote thing and then run tar or unzip to unpack it, just because it's easier to know what happens when you do that. Add is kind of legacy. We had add, and then we say, okay, we want something that has less magic, and so we implemented copy. All right. Volume, there will be a chapter on volumes, but volumes is a marker to say in this directory there's going to be persistent content that will change over time. Like typically for a database, you will tag the directory containing the database files with a volume statement. Workdir indicates that you want to change the current directory, because if you do run cd /home, okay, it goes to the /home directory, but it doesn't memorize that you are now in /home. So you can do run cd /home and then run whatever, and whatever will not execute in /home because Docker doesn't know that you moved to /home. So workdir is used when you want to change the directory for subsequent commands. Likewise, if you do run export variable equal value, yes, you set the variable in this specific build container, but then it's discarded. So if you want to set an environment variable, you have to use env. You can also set or override environment variables with docker run -e, like environment. And that's a common way to pass some configuration parameters to your container. User can change the UID. So by default, it's root in the container, but you can switch to a non-privileged user. We covered CMD already, as well as entry point. This chapter has kind of a recap of all the keywords, so it can be used as a standalone reference if needed, but interaction between CMD and entry point. And now I want to show, like, let's say, good and bad Dockerfile. And this is a common kind of mistake or thing that people do often. Like, this is, I will say, bad Dockerfile, but between quotes, because it's a very common beginner's mistake. So if you have a Dockerfile like that, let's say, so this is maybe a Flask web app, and so you have a requirements.txt that contains all your dependencies. And if you have something like that, each time you change something in your web app, even if you change like a little bit of JavaScript or a CSS, each time it will reinstall all the dependencies. And as if it's just Flask, it takes 10 seconds to reinstall, so that's okay. But once you have a big project and your dependencies take 5 minutes to install, very quickly you will get mad about Docker and be like, how can people even use that stuff? And so That is pretty easy to fix, but let's try to understand what's going on here. So okay, from Python, copy my whole repo into /src, then change the work directory to /src, then run pip install -qr requirements.txt. So that's where we install all the dependencies. And then I say expose port 5000 and execute python app.py as the default command. Let's say I change a small JavaScript or template or whatever, not even something code related. When I reach that line, it say, oh, you changed that file, so I can't use the cache. So I'm copying all the files in the container again, and I can't use the cache for all the subsequent lines. So no cache here, so I'm reinstalling all your dependencies. So TLDR, each time you change one file, you end up reinstalling everything. Compare with this Docker file, where now first I'm copying requirements.txt to my container, then I'm doing pip install requirements.txt, and then I'm copying the rest of the code. Now, if I change one line of code somewhere, copy requirements.txt, oh, requirements.txt has not changed, so we can use the cache. Next line, pip install whatever, we can still use the cache. Now copy .src, that has changed. So from that point, I will not use the cache and I will re-execute those steps, but those steps are really fast. So by going from that file to that file, I go from maybe 4 or 5 minutes build to a 4 or 5 seconds build, or even faster than that. So that's a really simple fix, but it will change the build time a lot. And also, of course, the bandwidth usage and everything, because you don't re-download the dependencies each time. Questions on that? Because this is like probably the biggest kind of annoying thing that you might have when you Dockerize your first stuff. It's like, my builds are slow and this sucks. And we've seen really bright and smart people do that and draw the conclusion that Docker was not suitable for them. So there is nothing to be ashamed of if this happens to you. And so I just want to make sure that you see like the idea behind this kind of little trick and how the caching system works. Yes? So why is it better? So let's make the comparison in the other direction. Let's say that I changed something in my code, but I didn't change requirements.txt. So I can go all the way to that point, and all those steps will be cached. Because since requirements.txt has not changed, Docker is able to use the result of the previous build. It's like, okay, this has not changed, so I can use the cache. I can use the cache. From that point, you've changed some files, so everything after that, I can't use the cache. But that's okay, because those steps are really fast. Compare with the other version. The other version is, the first thing I do is copy my code to the container. So if I change anything, like even an HTML template or whatever, Docker immediately says, okay, I can't use the cache because you changed something. Docker has no way to know that, okay, maybe you just changed a template, but it can't know that it doesn't affect your dependencies. So by default, it's like, you changed the file, so we have to rebuild everything after that line, which means it has to re-execute pip install requirements.txt. If we add requirements.txt first and run pip install requirements.txt, then Docker will reinstall requirements only when you edit the requirements.txt file. Does that make sense, or may?
So to clarify, you're saying the cache only sort of gets activated once in that case?
The cache only gets activated once. No, so the cache is dependent on the steps that were before. It's like, I can use the cache only if nothing has changed. In that case, as soon as you change a file, something has changed, so I have to redo all those steps. In that, sorry, wrong keyboard. In that case, I have to reinstall dependencies only if this has changed. In other words, only if requirements.txt has changed. It's just like in a makefile when you have, well, generally speaking, when you have dependencies, if you have a big, broad dependency, like, okay, this has to be done if anything in my project has changed, then each time you tweak a little something, you rebuild everything. Now, if you're like, okay, I know this has to be done only if that specific file has changed, now when you change anything else, you don't have to redo that step. Yep.
So what you're saying is, once the cache turns off, it's off for the rest of the build.
Yes, absolutely. Once the cache turns off, like if there is one step that can't be cached, then everything else has to, after that point, has to be rebuilt. Yes. This is because it's hard, maybe even impossible, to do a merge in a file system tree. I mean, yeah, technically you can do it. You could say, okay, let's execute that step and then reapply the other files. But most often times it will not do what you want.
So for the copy line, that means if I only change the one single file, then the copy, it will always copy the whole.
Yes, it means for the copy line here, when I do copy./src, if there is one file that changes in there, then it will recopy the whole thing, yeah. All right, so with what we saw so far, you can like already Dockerize stuff, and once you have built an image, you can upload it to the Docker Hub and use that to distribute it somewhere. I had a quick demo here, but I will skip it because we're kind of a little bit behind on time. But the idea is that you can create your account on the Docker Hub, then you do Docker push, and a few minutes later, the image is on the Docker Hub, and anybody can do Docker run on your image, and it will work. Okay. So now we're going to move to the second chapter, which is a little bit shorter, which is good, otherwise we would run out of time. And so in this chapter, we will be a little bit more on the ops side of things, like how do we, okay, now we know how to build containers, now how do we run all those containers? So first, naming and inspecting containers. So names are a way to identify containers. So instead of specifying the ID, you can put a symbolic name. So for instance, you can say the container running my production database will be proddb. So now instead of doing docker logs FAC09 something something, I can do docker logs proddb, docker stop proddb, and so on and so on. You might have noticed that in the output of docker ps, whoops, am I on the fast Wi-Fi? I don't even know. In the output of Docker PS, there are names, well, that's to Docker PS-A. And so, let's unzoom a little bit. The last column is a name. It's probably not readable here, but if you do that on your VMs, you will. And so those names are a mood and an inventor name, like Awesome Murdoch, Sick Kirch, if there anyone, you know, Adoring Perlman, and so on and so on. This is the name that is generated by default by Docker, and you can change that if you want. So, for instance, you can do Docker run -- name TikTok jpetazzo/clock, which means I want to give a specific name to my container. So now if I do docker ps-a, and I should probably look pipe head, and even that, it's, yeah. You can see that my container, instead of being named like NoTLN or whatever, is named like TikTok. Names are unique. It means that if I try to do the docker run -- name TikTok again, it will tell me, nope, the name TikTok is already in use by this other container. It doesn't matter if the container is running or stopped, the name has to be unique anyway. So how can I reuse that name? How do I create a container with that name? In that case, well, the obvious option is to get rid of the old container, like docker rm TikTok. And now I can do docker run -- name TikTok again. But what if I want to keep the logs of that container? If I do docker rm, I remove the container and its logs and everything. But in that case, okay, the container stopped and I want to find out. So I want to keep the logs. So another option is to rename the container. I can do docker rename TikTok, like TikTok underscore crashed. And then I can start a new TikTok container. All right.
Does your Docker client have to communicate with the Docker engine every time you do a run?
Does the Docker client has to communicate with the engine each time you do a run? Yes. Every single command, even when I do rename, it's not a local operation, it's remote. So if we were all of us like talking to the same engine, whenever somebody does Docker rename or Docker whatever, the others would see that when doing Docker PS. The local client has no state, no nothing. Yeah.
Does the RM command just remove the container but not the image?
Does the RM command remove the container but not the image? Exactly. RM will remove the container, but it will not touch the image. There is a RMI image, RMI command, sorry, to remove an image. And if you try to remove an image, but there are containers using that, it will tell you, you can't because this image is in use. Yes.
Like I see it now, but sometimes like if you do Docker images and you get like none and the tag is none, and I get that all the time, like at home when I'm like.
Right. Like when you do Docker images in the output, you see like, maybe we have it here. Yeah, we have a bunch of images with none. Like, what is that? That's when you build multiple times with the same name. Like the first time, it's like, okay, like that's the Figlet image. And those images below are probably the previous versions of the Figlet image. Each time you docker build -t Figlet, you kind of move the Figlet tag to something else. So and the images are still here because by default they stay here. So that, well, first, if you have containers using that image, they continue to run. And also because sometimes, and that's one of the big advantage kind of containers, is that if you start the container with the new image and you're like, oh, I messed up and I need to roll back to the previous thing, the image is still here. So you can very easily start the previous version. In that case, it's a little bit trickier because you have to identify, oh, that's probably this image. So generally, when you do that, you want to re-tag the old image to like Figlet:old, or you just keep all images with a specific tag, but the images are still here and they show up as none in that case, yeah. All right. Now inspect, so Docker inspect gives you tons, maybe a little bit too much of information on a container. Like I can do Docker inspect TikTok, and I'm going to pipe less, and so that's JSON, and there are like a ton of information. If you want to extract some specific information, of course you could do like pipe grep, pipe this, pipe that, but don't parse JSON with shell. It's easier than parsing HTML with regexes, but still it's not a good idea. What you can do is Docker inspect -- format. And so like that state that running, that should work, maybe. Whoops. Map, all right, so uppercase R, yeah. So what is this weird format thing that I'm doing here? So the double curly braces are the Go template engine, and dot will be the container object, and then you can drill down into the container object to extract the fields that you want. So in scripts, it's just easier to use that. All right. Okay, so that gives us some ways to script our containers, like we can start them and give names, and then we can inspect to see their state, their IP address, stuff like that. Speaking of IP addresses, how do containers do network stuff? Well, that's what we're going to see now. So the first thing we will do is that we're going to start a container that exposes a network service, and we're going to use an Nginx server for that. So I'm going to do docker run -d -p Nginx. So the -d means demonized or detached, so run that container in the background, and the P is shorthand for publish all. So it means take all the ports that are exposed by this container and make them public. How does Docker know which ports are exposed? Thanks to the Dockerfile expose instruction. Docker will not automatically know, aha, I see that there is a web server running on port 80 or 5000 or what have you. No, it will use that information in the Dockerfile. So when I do that, say, oh, what's this Nginx thing you're talking about? I'm going to check in the library. Why? Yes, we have an Nginx image, so I'm going to download it and run it. And now if I do docker ps-l, I see that I have an Nginx container. And here, in the ports column, I see two things. It's telling me 32769 is mapped to port 80, and 32768 is mapped to port 443. So in the Nginx image, there is some information telling this exposes port 80 and 443. And then Docker maps that on public ports, in that case, 32768 and 9. So if I go to my Docker VM, so I'm going to put the IP address here, on port 32769, I will see Nginx welcome page. Okay. So one question might be, all right, why are we mapping ports? Oh, yeah, by the way, if you don't like going into a graphic browser, you can also do curl localhost here, 32769, and that also works if you can parse HTML like visually. So why are we mapping ports? So if Docker had been something like 10 or 15 years ago, probably we wouldn't have bothered with that. We would just have said, oh, you want to run containers? Fine, you're going to have a class C network, you know, like a /24, a range of 256 IP addresses, and we're going to use that for your containers. Each time you start a container, boom, we give it an IP address, and you just connect to the IP address, and it's great. No port mapping, nothing like that. Except that works only if you have an infinite number of IP addresses available, which was kind of the case 10 or 15 years ago, except it was not exactly an infinite number. It was maybe billion or something, hundreds of millions. But at some point, that comes to an end. Today, IPv4 address space is kind of exhausted. There are still like kind of local pools of addresses here and there, but we know that eventually we'll be out of IPv4 addresses, and we should like be savvy with our existing IPv4 addresses. And in particular, today, if you say, hey, I have this server and I just want like 200 IP addresses on it, the answer will most likely be nope, no way. So we have to do with one IP address per server, and then we're using port mapping so that you can run a bunch of services on your server and expose them. All right. So now people might ask, okay, so you're running an Nginx container, and why can't we just map that Nginx container to port 80 and 443 directly? Why can't I just connect to my Docker machine on port 80 and get my Nginx container? At first, it sounds like a good idea. That good idea was also one of the biggest design mistakes that we made in the first versions of Docker. I mean, before it was called Docker, when it was like the engine for our pass. Why? Because if you do that, like the first time you start a container that is using port 80, it will happily kind of grab port 80 on the machine. And then the second container that you want to start that also needs port 80, you're like, what should I do? Oh, let's start it on a different port. Like let's take the next port, 81. Great. That was really a huge engineering mistake, because let's say I work on some web service. So I start it on my machine. It's going to be on port 80. So in the rest of my code, I'm going to say, okay, let's connect to port 80. Then somebody else in my team, another developer, also works on a web service, and she's also using port 80. So in her code, when she connects to port 80, she has her web service. Now we kind of share our containers, so I'm trying to run her service, but it will start on port 81. And when her code runs on my machine, when it connects on port 80, it hits my service instead of hers, and confusion ensues. So instead we decided, okay, you won't get port 80 automatically. By default, you will get a random high port number, and you have to check that port number and put it in your code or somehow, instead of assuming that it will probably be 80. That being said, if you really want to have something on port 80, no problem, you can do that with, so in that case, you use docker run -d -lowercase p, which just means like port mapping. So the first line here means map port 80 on the host to port 80 in the container. So that way you get Nginx listening on port 80 on the machine. Or you can do map port 8000 on the host to port 80 in the container. Or you can do map like you can map the same port multiple times, or rather you can expose a single port to multiple public ports. So here I want the port 80 of my Nginx container to be mapped to both 8080 and 8888. So how do we connect containers together, like, and how do we make them reachable from the rest of our applications? There are at least 3 ways to do that. First, there is like a docker run -p, so I tell Docker, pick a port or even multiple ports for this container. And then I can use the docker port command. Okay, so if I do docker ps here, and then docker port cf401, and I ask Docker, hey, where did you map port 80 for that container? And it's telling me on port 32769. And then I can take that and put that in my config files or parameters or service discovery so that the rest of my apps know where is my Nginx service running. I can also decide ahead of time, this thing will be on port 8000, and I can hard code it in my other configuration files. And in that case, I tell Docker, expose that on port 80, docker run -p 8000:80. And the last method is to use overlay networks, which are a mechanism so that you can have a bunch of containers sitting on a network where they can directly communicate with each other. And in that case, you don't need port mapping, but your containers are on a kind of internal network. So Docker has multiple network drivers for containers. The default one that we have been using so far transparently and without even thinking about it is the bridge driver. But there are also other drivers, and we can switch them with docker run --net. So the default bridge driver, each container has a virtual network interface with a private internal IP address, and it's connected to a virtual switch, technically a Linux bridge, sitting on the Docker host. If we look like on the Docker host, if I do ifconfig, I will see in the output there is like docker 0, that's the bridge. And then here veth blah 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 blah, that's the virtual interface going to my Nginx container. If let's say I start another Nginx container, and then I do ifconfig again, now I have 2 veth things here. And if I use like brctl show, that's the command to manipulate bridges on Linux. And then in that case, I see, yep, I have a bridge named docker 0, and it has 2 interfaces in it for my 2 containers. So if you are a Linux network expert and you want to kind of tweak things, you can do that with that easily. So containers are on an internal address space. They can access the outside world thanks to port mapping using a masquerade rule, and port mapping is done with IP tables DNAT. If you know IP tables, you know what that means. If you don't know IP tables, then you can blissfully ignore that. That's totally fine. Each container has its own network stack. This means that if you want, you could run like a VPN client or a firewall or a router or something like that in the container. That works fine. Now we have other drivers. There is the null driver. So for instance, if I do, okay, let's start a normal container. So docker run -ti alpine sh. Alpine it's a little bit bigger than BusyBox, but barely, but it's way more friendly to use. I do ifconfig, and so in this container, I have like a virtual ETH0 interface with an internal IP address. Fine. And if I like ping pycon.org, does that work? Yep. Now I'm going to run the same container, but with --net none. When I do that, that container doesn't have external connectivity. It still has a loopback, but if I do ping pycon.org, like, okay, normally it should me can't resolve. If I try to ping an IP address, it should tell me like network unreachable. Yeah. So this container is isolated from the network. What's the point? Well, sometimes you want to run some code and you want to make sure that the code makes no network access. So that's a good way to do it for isolation purposes. Or if you're like, oh, this thing is supposed to build without network access, but I want to make sure that it works because I want to be able to work on it in the plane, for instance, or some place where I don't have connectivity. Then we are going to step into weird territory. The host driver, so that one is way more like curious because now we are going to do stuff that we can't really do in the VM world. So I'm going to do --net host. When I do --net host, if I do ifconfig, in the output, you might recognize like those VETH interfaces, this Docker0 interface. Those are the host interfaces. But I'm still in the container. Like if I do PS, I only see the processes in the container. And this is an Alpine container, so there is no GPKG. I'm in my container, but I can see and use all the network interfaces of the host. If I use like netstat-ntlp, so to see all the listening sockets, those listening sockets are the sockets on the host, not the sockets of the container. So I have a container which shares the network stack of the host. What's the point? There are a couple of use cases. One of them is when you want to bypass this whole IP tables, bridge, etc., for performance reasons, like you're doing something that has a really high packet throughput, like VoIP or gaming, and you're like, oh, I want absolutely zero overhead on the network path. --net host will get you zero overhead. Or if you have a really high throughput, because you're doing like video streaming, same thing. Another use case is when you have an application that is kind of peer-to-peer, or at least it needs to be aware of its IP address. So you don't want to have that application running in the private container network. You want that application to sit directly on the host from a network standpoint. Then --net host gives you that. Okay. Next, and that one is going to be even weirder, --net container. All right, so with Docker PS, I have a couple of Nginx containers up and running. So I'm going to do the same Alpine container, but I put --net container, and the ID or name of an existing container. Let's say CF401, so that's the ID of this Nginx container. I do ifconfig. Yeah, it looks like I'm within a normal container. Everything is fine. Now, if I do netstat-ntlp, it's telling me that there is something listening on port 80, which is weird because if I check the processes in this container, there is nothing. So what is listening on port 80? Let's check with curl. Oh, right, I need curl. So apk add --update curl. So this is the equivalent of apt-get install or yum install with Alpine. All right, now curl localhost, and that's Nginx. So I'm in a different container, but I'm using the network stack of another container, which means that if I connect to localhost, I'm connecting to the other container. If I'm looking at open sockets or stuff like that, I'm seeing the other container. ifconfig, the IP address that I see here is the IP address of my Nginx container. In this container, if I set up routes or a VPN or something like that, it will also affect the Nginx container because they both share the same environment. If you want to give a really kind of rough metaphor on that, imagine like your containers are sitting right next to each other, but when you do --net container, it's as if they were like both next to each other and remove the wall between them, so now they have the same network stack. Everything else is different. Like one is Nginx running on, I don't know, maybe it's Debian or something like that. The other is an Alpine container. They could have different processes running, they could have different memory limits, they could have different whatever you want, but they have exactly the same network stack. All right, so that was like some basics on networking. And why would we use that? Yeah, fair question. So there are tons of use cases for that. Like one of them is I have this service that either needs to connect to a VPN or needs to be reachable from the VPN, but I don't want to put the VPN client in the container because, well, maybe that's like some Python service or whatever, and I like to work on Debian or Ubuntu, but the VPN client only works on CentOS, or at least it's certified only on CentOS or whatever. In that case, I can run the VPN client in a container and then start the web server with this --net container thing. And that way, my web server is completely oblivious to the fact that there is a VPN thing. So that helps me to decouple the complexity. And so I have VPN container and then the other container. That can also be used like for stuff like Tor, so that you can connect to the Tor network or be reachable through the Tor network, but without installing Tor in the application container. Other scenarios include like setting up QoS, traffic control, custom routing. You can do that in a different container. But the application container is like, I'm just here, I'm using the network stack, but I didn't need to set up anything. That's just a small sample of the use case. Oh, another one is when you have like some admin interface and you don't really want to expose it, but you still want to be able to access it. In that case, you say, okay, the admin interface is going to be on localhost, and if I want to connect to it, I'm going to use the --net container thing. So now I'm kind of breaking into the container and I can connect over localhost. And one last example is when you have like a web front end that wants to talk to a database or cache or whatever, and you want to do that with a really good performance, latency, etc., you can start them both in the same network stack, so they can talk over localhost and bypass the whole virtual network interface, port mapping, Linux bridge, whatever. And when you connect over localhost, the bandwidth is pretty good. So that's the few use cases. But people come up with fancy uses for that all the time. It's just weird the first time because it's like, what? All right, so let's ramp up from that and let's talk about the container network model. So the container network model is the kind of model that we have when you want to have a bunch of containers talking to each other, and you don't want to encumber yourself with the port mapping. So in that model, you can create a network or even multiple networks, and then you can connect those containers to one or multiple networks, and then they can communicate directly with each other in this private network. So for instance, if you do Docker network ls, you see like the default network. So there is the bridge network that is used by default, the host network, we cite with --net host, and the none network, which corresponds to I, in fact, don't want a network at all. But you can also create your own network. So here, for instance, we can see like there is a blog dev and blog prod network. What exactly is a network? A network is like a virtual switch, and you connect containers to that virtual switch. Each network will have a subnet, a range of IP addresses, which is picked automatically by Docker, but you can also force that to something specific. If you want, like if you are one of the lucky few who still have IP addresses, you can assign a range of public IP addresses to your network, and then when you place a container on that network, Docker will automatically allocate an address in the network to the container. each network is managed by a driver. And so those drivers allow you to put containers on other kinds of network. What I mean here is that there is like this bridge driver, which is like a local network for your containers on a single host. But there is also a driver called overlay, which lets you have a network spanning multiple hosts. And then it's kind of magic. It's a little bit like a multi-point VPN, if you want, where you could have like a bunch of Docker machines, and you have containers running on a single overlay network, and they can talk to each other over this network. You could also have custom drivers. For instance, if you have like a good old physical Ethernet network and VLANs and DHCP, you could have a custom driver. And when you do like docker run --net VLAN 42, then it's going to join VLAN 42 on your physical network interface. It's going to make a DHCP request there, and it's going to allocate to give this IP address to your container and connect your container to this network. So you can do pretty much anything you want with those custom drivers and to integrate containers within existing infrastructure. All right. So how do we manipulate those networks? I'm going to like Docker network create dev. That's how I create a network. And now in Docker network ls, I see I have a new dev network also using the bridge driver. And now I can do like docker run --net dev and start my containers. All right. So we are going to put a container on the network. So I'm going to do docker run --net dev. I'm going to give it a name, --name search, -d to put that in the background, Elasticsearch. So this will pull the Elasticsearch image, and then it will run it in the background. And then I'm going to start another container on the same network. So I do docker run --net dev -ti, let's say CentOS. And now I can do ping search. That works. So the containers will be reachable using their names. I can do curl search on port 9200. That's the default port for Elasticsearch. And that gives me like the little kind of ping API endpoint for Elasticsearch, which tells me, hey, hello, that's Elasticsearch here, and I'm up and running. Okay. So now it means in my code, when I want to connect to Elasticsearch, I can just use search :9200 as the URL, and it will work because Docker has an embedded DNS server that exposes one different view for each network. So on the dev network, the search name corresponds to this container. So how do I connect multiple things together? Like, let's say I have a little demo app that has a web front end and that is using a Redis backend. So my demo app is jpetazzo/training wheels, and I'm going to start that on the dev network, and I want to expose all ports. So docker run --net dev -d to put it in the background, --P because I want it to be reachable from outside, jpetazzo/training wheels. It's going to pull the image. This is a little Python Flask app. I'm going to do docker ps-l to see on what it's exposed. It's exposed on 32.770. And so if I go to 32.770 on my Docker VM, I get like a big red error page that tells me connecting to Redis on port 6379, name or service not known. If I were to go look in the code for that, it's on this GitHub repo here. In the code here, I have like Redis equal Redis.Redis. So it's trying to connect to the name Redis. Here in like classic code, we would have something like maybe the IP address or the full name for the Redis service. But here we just have the name Redis. And as a result, when I try to run that, it tells me, well, you're nice, but Redis doesn't exist, so that thing is not found. So how do we make that available? Well, I'm going to start a Redis container on the dev network with the Redis name. So docker run --net dev --name Redis -d to have it in the background, and I want the Redis image. I do just that. Now I reload, and boom, it works, because this time it goes over again in the code, and when it tries to connect to Redis, it resolves the name Redis. And since I created a container named Redis, now the Redis name resolves to the IP address of this container, and now my Flask application can connect to Redis and can serve me this web counter. All right. Okay. So each network has its own view of the names. So if I want, I could create like the prod network, and in the prod network, Redis could point to a different container. So that's great, because I can run the same code, the same containers in different networks, and each time they would connect to their local Redis service. However, if you remember well, names are unique. So I can't do like docker run --net prod --name Redis. It will tell me, no, Redis name is already taken. You can't do that. So there is another option, net alias, which, as the name implies, is used to set a network alias, but not a name for the container. So if we did that, then we would create a container that would not be named Redis, but that would be reachable with the name Redis in this network. Docker will not create those names and aliases in the default bridge network. So you have to do docker network create blah and then docker run --net blah for this to work. The reason why is because those names and aliases were added in like Docker 1.9, and we didn't want to change the behavior for older versions. So you have to create a custom network if you want names. In recent versions of the Docker engine, if you create multiple containers with the same network alias, like for instance, let's say do docker run --net dev -d --net alias search Elasticsearch. Let's say I create a couple of other containers with that name. So now I go in the dev network with an Alpine container, and I do like nslookup search. It will resolve to all the IP addresses of the containers that have this search alias. So if I do curl search :9200, well, okay, add --update curl. You might get some kind of load balancing, but it's not guaranteed, because like in that case, normally if you get some load balancing, the name here would change at each request, but the resolver sorts the IP addresses it receives, so in that case it's always connecting to the same one. But when you resolve here, you will see that the resolving search gives you all the backends for this container name. So this mechanism, like creating a network and placing containers on the network, out of the box, it works on a single machine. But if you deploy a key value store like Zookeeper, Console, or etcd, you can set up an overlay network that will let containers talk to each other across multiple instances. And that's one of the things that will be covered in the advanced tutorial this afternoon. All right, there is another mechanism that you should know about, but not necessarily in depth, called links. And that's the legacy thing that existed before the overlay networks. So the key difference between links and overlay networks is that when you create an overlay network, you can create containers in any order you like. Like here I created the web server, and I was like, oh, I need a Redis too, and then I created the Redis. I could also create Redis and then create the web server, and I can even like replace them, and I can do whatever I want. With links, it's different. You have to create the server, so the thing that accepts connection first, and then you have to create the client and give a special option to say, I want you to be able to connect to that. And I have like a big slide showing all the differences, but you can safely ignore links. This is just here, like if you look into some existing Docker app and suddenly you see like links, what is that? Then that's when you can learn about it. But otherwise, it's safe to ignore them. All right, questions on network? Yeah.
So when you do that alias, is it using bind or is it using like bonjour protocol?
Right. So when we do those aliases, which DNS server is used? It's a small DNS server embedded inside the Docker engine. So I don't know if it's from scratch code or if it's using some DNS library. I assume the latest, but it's embedded within the Docker engine. So it's not bind or DNS mask or anything like that. It's a full-blown DNS resolver inside the engine. How do we get redundancy? You mean for the DNS resolving itself? So for the DNS resolving itself, the DNS resolver is local to the container. So basically, if I'm in a container and I try to resolve the name search, if that doesn't work, there are, let's say, 3 possible outcomes. Either it's because search doesn't exist, so yeah, okay, in that case it shouldn't work. Or because the engine is down, but if the engine is down, my container is most likely down too, so it's kind of a non-issue in a way, or because there is a bug in the engine. But for that specific software component, we don't really need redundancy because it's supported by the same machine as the container itself. So it's like, if it's down, it's because the machine is down, and if the machine is down, then the container is down, so the client doesn't exist anymore. Does that make sense? All right, so we are now going to see how to implement a local development workflow with Docker, so what it looks like to develop things with Docker. And what we're going to do is to share a directory between the host and a container. The idea is to have a clean dev environment that comes pre-installed with all the libraries and all the things you need, and you can just like share that and use that as a dev environment. And here, to make that more palatable, we are going to have a Ruby example, because if it's a Python example, like most of you will be like, yeah, that's pretty useless. We could just do a virtual env and call it a day, and that would work. So on purpose, we say, okay, this is a Ruby example, because that way you're kind of pushing ourselves a little bit out of our comfort zone and resist the temptation of just running it locally. So that's the application that we will use, jpetazzo/namer. So I'm going to first like run it to see what it looks like. Docker run -d -p jpetazzo/namer. So it's going to pull that image. All right, and now if I do docker ps-l, I see that it's exposing something on port 32771. So I'm going to my EC2 instance on port 32771, and that gives me like in blue, like there is a title and a motto. So this application is an enterprise grade enterprise name generator with a tagline. And it's blue, which is important for the next step. So now, let's say I coded this for a customer, and the customer is saying, okay, the app is nice, but I want the text to be in red. So I have to make changes in the code. So I'm going to clone the code repo for that. So git clone, git :// well, first let's go to the home directory. Git clone, git : / github.com, jpetazzo namer. So in this namer application, I have a Docker file. The Docker file like copies the source code into /src. It's using bundler install, which is the equivalent of pip in the Ruby world. It's executing rackup. If I look into the gem file, which is the equivalent of requirements.txt, I see that it's installing Sinatra, which is the equivalent of Flask, more or less, a couple of other modules. So I have a bunch of things, and my code is in company name generator.rb, and all I want to do is change this thing here from color blue to color red. So with what we saw up to now, what I could do is I could make the change, rebuild the container, and restart. But I want to see how I can make changes without having to rebuild each time. And for that, I will run this command here. So let's see what each of those parameters mean. So docker run -d in the background, -v, $pwd :/src. So -v means volume. I'm going to bind mount a path on the host to a path in the container. So I'm bind mounting the current directory where there is my application code to /src in the container, because look at the Docker file here, we are copying the application code to /src. So I'm kind of overwriting, masking the application code in the container with the application code that I have locally. Then -p 80:9292. So I'm mapping port 80 of my Docker machine to port 9292 in the container, because 9292 is the port where the web server is running. And jpetazzo /namer. So I do that, and now I can go on port 80 here. So I get the same application, generating like silly names in blue. So now I'm going to change the code. So here, instead of blue, I'm going to put red. I'm saving my changes. I go back to my browser, I reload, and now it's red. If I go back to the one that is running on port 32771, so this one is just running the plain image without -v or anything, that one is still in blue, because that one is still running like the, let's say, static code. So it's completely impervious to whatever changes I could do locally. But that other one here is running a live version of the code, if you will. Like if I do further changes, let's say I put green, and I save, and I reload, no, it's green. So this gives me a really easy way to do some fast iterative development, because this directory is mapped into the container, is shared with the container, so each time I change something, instantly is changed in the container as well. All right, viewing the app, changing from blue to red. So that's nice, because okay, we have this command that maps the source code into the container, but you have to give your team like the whole command line. You have to tell them, okay, so you have to do docker run -d -v this -p that, blah 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 blah. So the next step is to have a compose file that will kind of capture that entirely. Remember, in the very beginning, I said fast onboarding. You just do docker, you git clone the repo, you do docker compose up, and it works. Let's see if this is true. I'm going to do docker compose up and -d, because I want to start the stack in the background. And when I do docker compose up, it's downloading the base images, it's building my container image. Then, so here you can see like the Docker file, so that's bundler install and this and that. And yeah, it's complaining because there is already a container running on port 80. So that's what you get if you try to put multiple containers on the same port. It will complain because the port is already in use. So I do docker compose up, and now on port 80, I have my application. I can still change that from green to yellow. So yellow on a white background, I'm pretty sure it will be impossible to read. Yep, fair enough. And so the advantage of using Compose is that instead of having instructions saying you have to do docker run with a bunch of complicated parameters, and those parameters get more and more complicated as the application gets more complex, now you just tell them docker compose up -d, and that's it. So how does that work? When you do docker compose up, it will read the docker compose file, which looks like this. It says we have a www service which is built using a Docker file located in the current directory, and we want to mount volumes. We want to mount the current directory to /src, and we want to expose port 80 on the machine to port 9292 in the container. And so the idea is that you almost don't even need to have documentation for that, because when you get that repo, you look at it and you know, like when you have a make file, you know you can try to do like make install. When you have like a requirements.txt or setup py, you know you can try like pip install and Python setup py install. When you have a Docker file, now you can try to Docker build. When you have a docker compose.yaml file, you can try docker compose up and it should work. Okay. So the general idea to have a nice development workflow is that you have somebody that will take care of writing the Docker file and then possibly the compose file, and then the rest of the team just has to do Docker compose up and things work out of the box. Volumes can be generalized. So here we're just mapping the source directory inside the container, but generally speaking, volumes are a way to store writable content. So we saw like in the Docker file section, you can declare volume, and this directory will be a volume, and when you have a database, you should kind of tag the directory containing the data files with the volume instruction. It will keep that directory outside of the normal file system of the container. This lets you do, for instance, if you want, you can start a container in read-only mode. In that case, the container is read-only, so it can be changed. That's a huge security improvement. But if that container is a database, you still want to be able to write things, so you can have a volume, and then in that case, you will be able to write in the volume. There is one particular example that I want to show, which is bind mounting. Like there is a few examples about that, but we can skip ahead that. So you can bind mount a single file, and here I want to bind mount the Docker control socket. So remember I said when you do Docker whatever, you are sending an API request to Docker engine, and by default, you're talking over a local Unix socket. So it's not a TCP socket, so it's not host and port. It's a Unix socket which exists as a pseudo file on the file system, and by default, it's /var/run/docker.sock. Yeah, sorry. Yeah, too many things in that directory. It's a special type socket. So we can share that with a container. Example, I can do docker run -ti -v var run docker.sock var run docker.sock. So it means take that Docker control socket and expose it in that container. And then what container image do I want to run? I will want to run the Docker image. So the Docker image is an image that contains a Docker binary. And now, so I'm in a container here, but if I do docker ps, I'm talking over the Docker socket, so I'm talking to the Docker engine that is running my own container, which means that if I do, for instance, docker kill on this container, this is the container in which I'm running. So if I do that, I'm basically sawing off the branch on which I'm sitting, and I'm getting back to the host. So this is not just like a nice party trick. This is super useful when you want to have a container running, for instance, like CI or builds, and you want to, that container, like let's say you run Jenkins. So you want Jenkins to be in a container because obviously, but you want Jenkins to build and start other containers. So the first thought would be, okay, maybe we need to do Docker in Docker. And yes, you can do that, but you shouldn't, at least not in that specific scenario. It's way better to just expose the Docker control socket to your Jenkins container so that now your Jenkins container can talk to the Docker API. There are a bunch of volume plugins available as well, so that you can have volumes hosted on like external storage, on either like physical, actual SAN, NAS, or cloud storage like EBS and others. So this is just like if you want to explore what's available for volume and storage. And the last chapter, I'm going to cover that really quick since we are 2 minutes behind. So Compose, I covered Compose like briefly to show, okay, Compose gives me a way to describe the parameters for Docker run. Compose can also be used for stacks of multiple containers. And I'm going to show the example with the training wheels application. So git clone, git colon / github.com jpetazzo training wheels. There is a compose file, and in that compose file, it says I have a www service and I have a Redis service. And so now when I do docker compose up, it's going to build whatever needs to be built, and then it will start both containers, the www container and the Redis container together. So when I have a complex stack, when I have like a web front end, and I have an API backend, and I have Redis, and I have Postgres, and maybe even Elasticsearch, and a bunch of things, I can have all that in my compose file. And when I do docker compose up, it will build all the containers that rely on code and start all those containers, and they will all be on their local private network talking to each other, which is great because if I need to run the same app, like 2 versions side by side to compare like what's changed or whatever, I can do that super easily. I just like make a copy of the repo and do docker compose up as well, and now I have 2 copies of the app running side by side. All right. There are some information on Compose here, but basically the Compose has like Docker Compose up, Docker Compose PS to see the containers running in my stack, Docker Compose build to force a build, Docker Compose stop, Docker Compose kill, and so on, Docker Compose logs. All those commands kind of follow the same syntax as Docker. And that's pretty much it. There will be more details on Compose this afternoon. Out of curiosity, who's going to be in the advanced tutorial this afternoon as well? Okay, maybe 1/3 of the people. Okay. Yeah, that's pretty much all I have on Compose. So this is a bunch of links, extra information. Thank you for being wonderful students today. If you have a few questions, I will stay here and then head off to lunch. You can also like ping me after the tutorials. Thanks a lot.